In database management, mastering key tools and techniques is essential for building efficient, secure, and optimized systems. This course, Database Integration and Management, will guide you through foundational concepts like setting up and modeling relational databases with Entity Framework Core, also known as EF Core, and performing essential CRUD operations. You'll also work with SQL for data retrieval, explore advanced techniques, and leverage Microsoft Copilot to enhance performance. Let's get started. We will begin by introducing the features of Entity Framework Core, also known as EF Core, and the key principles of relational databases. You'll learn how to set up a database, model data using EF Core, and perform essential CRUD operations to interact with databases effectively. Next, you'll explore the basics of SQL, starting with its syntax and core functionalities. You'll learn how to retrieve and manipulate data using select, insert, update, and delete statements. We'll also cover the use of join clauses to combine data from multiple tables and explore SQL functions and aggregate functions. Then, we'll move on to advanced data handling techniques, concentrating on advanced SQL queries and performance tuning strategies. You'll understand how to manage transactions, concurrency control in SQL, and stored procedures and functions. We'll also cover best practices for securing SQL databases. Finally, you will explore how Microsoft Copilot enhances database operations from writing and debugging SQL queries to generating complex ones. You'll learn how to optimize query performance with Copilot and apply it in practical database operations for greater efficiency. By the end of this course, you'll have the skills to manage relational databases, perform essential CRUD operations using EF Core, and apply advanced SQL techniques to optimize performance. You'll also know how to enhance database operations with Microsoft Copilot, making your workflows more efficient and secure. Let's get started. Hello, my name is Tyler Morgan, and I am one of your instructors for this course. I've been a developer since 2011 when I started writing my first applications. However, my journey with programming began much earlier. I first tried to learn programming back in 1999 when I was in the 7th grade because I wanted to build a video game. I eagerly picked up books and tried to learn on my own, but I failed miserably at even grasping the basics. The main reason was that I didn't have anyone to guide me and show me what I needed to do. This experience scarred me so much that I didn't attempt programming again until I was in college when I was required to take an introductory programming course. In that course, I finally learned the very basics of programming. It gave me the confidence to believe that programming was something that I could tackle. The problem was that while I understood the syntax of programming, I still didn't know how to turn if statements and for loops into software. It wasn't until I discovered online courses that my abilities as a developer really took off. These courses held my hand a little bit, showing me what I needed to learn and steering me away from topics that were too advanced for my experience level. Thanks to the help of these courses, I began to understand how the web worked, how to build software, and how to turn the things in my imagination into reality. I was so enamored with online learning that I went to work for an online education company, building their alumni network. That work gave me the confidence to break out on my own as a software developer. I started a company called Numerite, where I did cutting-edge web-based visualization work for the federal government and groundbreaking machine learning for university researchers. And I created awesome tools for huge companies. Then a few years ago, I had the opportunity to fulfill my dream of starting a farm. Now you might think farming has very little to do with software engineering, but it's amazing how handy it is. I wrote my own software to manage crop planning, built our website, and integrated with external services to create the functionalities that my customers wanted. I created entire data pipelines to ingest local market data and determine where there were gaps in local agricultural production. I'm sharing all of this with you because learning how to be a developer isn't just for those who want to work for big tech companies. It's an amazing tool for anyone. And with proper guidance, you can learn what took me decades in just a few months. So let's get started.
The learning experience in this course is designed to give you a comprehensive understanding of key concepts through various learning methods. You'll be guided through interactive, engaging materials that help you build practical and theoretical knowledge. Whether you're interested in front-end, back-end, or full-stack development, this program has the tools to support your growth every step of the way. Throughout the course, you'll be introduced to core concepts and key ideas in videos. These videos are designed to help you understand definitions, processes, and essential steps clearly and concisely. You'll get to absorb foundational knowledge, setting the stage for deeper exploration as you move forward. And when you need step-by-step guidance, screencasts will provide you with a detailed practical view. These screencasts will show you exactly what's on the screen and how to work through specific coding tasks. The course also includes readings that reinforce the key ideas presented in the videos. These readings are more than just supplementary material, they're job aids. You can print them out and use them as a reference while working on assignments or activities, helping to apply what you've learned in real-world situations more easily. Small activities are included to help you check your understanding of key ideas. These activities provide quick, interactive opportunities to practice what you've just learned. After completing each activity, you can compare your work with a fully explained example and answer key. This ensures that you always know if your answer is correct. Practical experience doing tasks you would in a job within this field is essential, and that's where guided labs come in. These labs take you through the implementation of different concepts step by step. As you work, you'll receive feedback and helpful hints, ensuring you can get the help you need when you need it. It's the perfect opportunity to practice in a controlled environment while learning by doing. After completing the guided labs, you'll move on to independent projects, or you try it. This is where you'll put your skills to the test, applying what you've learned in the labs. You'll work through real-world problems, cementing your understanding of the course material. The course will culminate in a practical project leveraging Microsoft Copilot that you can use as a portfolio artifact when you begin your job search in this field. As you progress through the program, the portfolio pieces will become stronger and better representations of the authentic experience you've gained. They'll showcase your understanding of code and the ability to implement different concepts from the developer program. This course guides you step by step from understanding concepts through videos and readings to apply them in activities, screencasts, and labs. Each part of the course builds on the last, helping you gain knowledge and authentic experience. By the end, you'll have completed real projects that not only showcase your skills, but can also be included in your portfolio as you start your career. Everything you do here will prepare you for success as a developer. Let's get started.
Throughout this course, you'll complete several guided labs. These labs are meant to give you an opportunity to practice your newly learned skills in an environment where you can get help and feedback as you complete coding challenges. This video will describe how to complete the guided labs in this course. We will explore a guided lab together so that you'll know what to expect when you come to one later in the course. First, let's check the content leading up to a guided lab. This structured content ensures that you have exactly the skills you need to complete the task. In this instance, there is a practical application video that describes in detail how this concept is used in real-world situations. Following this practical application video, you can review a reading that explains the concept in detail so you can go through this content at your own pace. Next, you'll find a video that works through the guided lab itself. This video won't give you all the answers to the guided lab, but it will provide an overview of the upcoming questions and challenges. Lastly, we come to the guided lab itself. The guided lab is a simulated code environment where you can experiment with code and receive hints and feedback in a realistic coding situation. To start, I'll click Start. In this lab, step 1 is an introduction to if-else statements, so I'll click Begin. Below the simulated code environment, I can find the specific instructions for this lab. Declare the variable age as type int. Place your cursor into line 2, type your answer, and select Enter to check your work. Alright, I think I know this one. I'm going to type in INT and hit Enter. Great, I got that correct, and I got a bit of feedback about my correct answer. To move on, I click Continue. And these instructions say, prompt the user to enter their age, place your cursor into line 4, type your answer, and select Enter to check your work. This one is a little trickier. Let me try type your age. Got it. This feedback for my wrong answer points me in the right direction. Let's try that again. I'm going to erase what I had here and then enter your age. Perfect. I'll click continue. Let's try one more. Convert the input to an integer using int.parse and store it in the age variable. Place your cursor into line 6, type your answer, and select enter to check your work. I'm not totally sure here, so I'm going to click on hint and get some help. And the hint says use console.readline and then an open and close parentheses, display a message asking their user for their age. Great, that helps. I'm going to click continue and type in console.readline. And I've got it. That's how you work through a guided lab. Some questions will require more complex code to complete, so make sure you're using the hint function when you need it and reviewing the feedback provided for your right and wrong answers. Have fun completing these coding challenges that put your new skills to work.
In today's rapidly evolving tech landscape, artificial intelligence plays a key role in making development more efficient and intelligent. That's where Microsoft Copilot comes in. Microsoft Copilot is a powerful AI-driven tool that can assist developers in writing, optimizing, and debugging code. In this course, you'll leverage Copilot as a thought partner and a code-generating assistant, helping you solve problems, generate code snippets, and enhance your projects. The goal is to provide you with hands-on experience using a tool that real-world developers use to improve their workflow. In the last module of this course, you'll engage in videos, screencasts, guided labs, and independent projects that integrate Copilot. These labs will take you through how to use specific prompts to generate code, optimize solutions, and solve problems. You'll be shown step-by-step how to leverage Copilot's capabilities to strategically approach the final project. During the guided labs, you'll get hands-on experience working with Copilot. These labs are structured to show you how to craft effective prompts and work with Copilot's code generation features. You'll use it to assist in writing code, refining your solutions, and debugging. This practice will prepare you for the independent work you'll do in the final project. After the videos, screencasts, or guided labs, you'll move on to independent activities where you'll take control. Here you'll use Copilot to assist with various aspects of the project. You'll be making strategic decisions, but Copilot will support you by generating code, suggesting optimizations, and helping you troubleshoot. This prepares you to work more independently while still having the power of AI to assist. The final project will combine everything you've learned in the course, and you'll have Copilot as a key tool in your development toolkit. You'll use Copilot to help you generate and refine code as you combine the concepts from earlier lessons. The project is a portfolio-ready artifact showcasing your coding skills and your ability to leverage AI in modern development workflows. To succeed in the final module, actively engage with the guided labs and practice using Microsoft Copilot effectively. The videos and prompts will take you through Copilot and equip you to apply it strategically and independently. By the end of the course, you'll be fully prepared to complete the final project and demonstrate your skills using traditional coding and AI-assisted workflows. Welcome to the course. In this video, we will discuss how you can make the most of each part of the course to set yourself up for success. Whether you watch the videos, complete activities, or work through hands-on labs, each element has been designed to help you master the skills you need to become a confident and capable developer. The first step in every lesson is the videos. You'll be introduced to new concepts, definitions, and key ideas. Watch these carefully and take notes on the important points. The videos provide the foundational knowledge you'll need to build on, so don't skip them. They'll give you the context to understand everything that comes next. After each video, complete the readings. These readings reinforce the key ideas you've just learned and can serve as job aids. I recommend printing out the readings or saving them for quick reference. They'll be extremely helpful when completing activities, working on projects, or just needing a refresher. They're not just supplementary. They help you apply what you've learned to real-world tasks. Throughout the course, you'll find small but impactful activities. These quick exercises allow you to check your understanding of key ideas. Don't rush through them. Take the time to work through these activities thoughtfully. After each, compare answers with the answer key to check how well you understand the material. This is your chance to practice without pressure. At the end of each lesson, you'll encounter practice quizzes. These quizzes are a great way to ensure you fully grasp the concepts from the videos and the readings. Use these as a checkpoint to assess how well you retain the information. If you find yourself struggling, review the videos and readings again. The goal is to build confidence and solidify your understanding before moving forward. When you need to see the material in action, screencasts guide you. These videos show you exactly how to work through certain tasks step by step. If you ever feel stuck or unsure about applying a concept, watch the screencasts and follow along. This hands-on guidance is invaluable for understanding how the code works in real time and applying what you've learned. At the end of each module, there will be graded quizzes. These are an important part of your success as they allow you to demonstrate mastery of the material. These quizzes build on the practice quizzes, and they're a great way to ensure you're ready to move on to more advanced concepts. Treat these quizzes as milestones. Passing them means you're fully prepared for the next challenge. The guided labs are where you'll take the concepts from the lessons and apply them in a controlled, hands-on environment. These labs will take you step by step through tasks, including helpful feedback and hints. The more effort you put into the labs, the more you'll get out of them. It's all about learning by doing, so take your time and ensure you understand each step before moving on. After you've completed the guided labs, it's time to test your skills with independent projects or U-Try-Its. This is where you'll apply everything you've learned without step-by-step instructions. These projects are a great way to gauge how far you've come and to put your knowledge to the test. Don't worry if you feel challenged, that's part of the learning process. By completing these projects, you'll reinforce your skills and build confidence. Finally, at the end of the course, you'll complete a culminating hands-on project that you can use as a portfolio artifact. This project will showcase the skills you've gained throughout the course and give you something tangible to present to potential employers. As you progress through the program, these portfolio pieces will become stronger representations of your hands-on experience and understanding of key concepts. Success in this course comes down to using all the tools available. Watch the videos carefully, engage with the readings, complete the activities and quizzes thoughtfully, and take full advantage of the screencasts, labs, and projects. Each element of this course is designed to help you master the material step by step. By the end, you'll have a solid understanding of the concepts and real projects to prove your skills. Remember to persist, take your time, and you'll be ready for a successful career in development. Are you ready to take your database skills to the next level? By the end of this end-of-course project, you'll have developed a high-performing database system for SmartShop, a dynamic inventory management solution designed to showcase your back-end development expertise. Whether you're creating this system to impress potential employers, deepen your knowledge of database design, or simply test out your new skills, this project is your chance to shine. And don't worry, you won't be doing this alone. Microsoft Copilot will be your sidekick, helping you write, debug, and optimize your SQL queries every step of the way. In this video, we'll introduce the end of the course project. By the end of the project, you'll have developed a comprehensive database system capable of managing inventory data, analyzing sales trends, and streamlining operations for SmartShop. Using SQL and Copilot, you'll write efficient queries, optimize database performance, and generate actionable insights. Copilot will assist you throughout the process, making your workflow smoother and more efficient. Whether you're new to SQL or have some experience, this project is designed to be approachable and help you build essential back-end development skills. Let's explore the details. The goal of this project is to create the Smart Shop inventory system, which will include the following components. You'll create basic SQL queries to retrieve and filter inventory data, including product details, stock level, and pricing. Then you'll generate more complex queries and use joins, nested queries, and aggregation to analyze sales trends and supplier performance. And finally, you'll debug and optimize your SQL statements to ensure scalability and efficiency for large data sets. Throughout the project, you'll use Microsoft Copilot to assist with generating SQL queries for data retrieval and manipulation, debugging errors and resolving performance bottlenecks, and optimizing queries for faster execution and better database performance. You'll progress through a series of structured activities, each aligned with lessons you've completed in this course. This project is broken into 3 activities. In Activity 1, you will use Copilot to generate basic SQL queries to retrieve and filter product, sales, and supplier data. Then in Activity 2, you'll create complex SQL queries involving multiple table joins, nested queries, and aggregation for advanced data analysis. Finally, in Activity 3, you'll debug and optimize your SQL queries to improve accuracy and performance, ensuring the database system can handle real-world demands. Each activity builds on the previous one to ensure a structured learning experience, and Copilot will be your guide at every stage, offering real-time suggestions and enhancements. You'll follow detailed step-by-step instructions, and by the end of the project, you'll have a robust and efficient inventory management system that you can proudly showcase in your portfolio. Plus, this project demonstrates your proficiency in SQL and your ability to leverage AI tools like Microsoft Copilot for back-end development. This end-of-course project is your chance to bring your ideas to life and showcase your skills. It should be a challenging but satisfying experience.
In this module, you'll learn how to use Entity Framework Core, EF Core, and relational databases, essential skills for managing data in modern applications. Mastering these tools will enable you to efficiently set up databases, model data, and perform CRUD operations, making your back-end systems more robust and scalable. We will begin by exploring Entity Framework Core's features and functionalities and understanding its role in database management. Next, we will learn the fundamentals of relational databases, focusing on their structure and key principles. Then, we will examine setting up a relational database, covering its necessary steps. After that, we will examine data modeling with Entity Framework Core and learn how to represent data with the framework effectively. Finally, we will perform basic CRUD operations, utilizing SQL and aggregate functions to manage and analyze data. By the end of this module, you'll have the skills to efficiently manage data using Entity Framework Core and relational databases, empowering you to build scalable, robust back-end systems. Let's get started with Introduction to EF Core and relational databases. Managing data manually in an application can quickly become overwhelming. Every time you need to store, update, or retrieve data, you'd have to write repetitive code, carefully handling each operation on your own. As your application scales, this approach becomes inefficient and error-prone, making even minor changes a significant task. And that's where object-relational mapping, or ORMs, come in. In this video, we will explain the concept of object-relational mapping and the role of EF Core as an ORM tool. Before discussing ORMs, let's define relational databases, a key part of object-relational mapping. A relational database is a structured collection of data organized into tables, where each table consists of rows and columns. The tables are related to each other through identifiers, enabling efficient data retrieval, manipulation, and storage using structured query language. Structured Query Language, or SQL, is a computer language used to communicate with and manage relational databases. Think of SQL as the language you speak to interact with databases. For example, a table in a library database might have columns for book titles, authors, and the year the book was published, while the rows represent individual books. In the first row, we might have To Kill a Mockingbird by Harper Lee, published in 1960. This row and column structure makes relational databases powerful tools for managing data efficiently. However, let's consider how we typically write code in object-oriented programming languages like C#. In these languages, we represent data as objects. In C#, we represent data using classes and objects. For example, we might have a book class in C# with properties like title, author, and publication year. To represent this as an object, we might have an object called book1, with the values To Kill a Mockingbird for title, Harper Lee for author, and 1960 for publication year. This creates a mismatch between the way we structure data in code as objects and the way databases store data as tables. To access or store data in a database, we would normally have to write many SQL queries to manually translate between these two formats, which can be time-consuming and error-prone. This is where object-relational mapping, or ORMs, come in. ORMs are a programming technique that converts data between object-oriented programming languages like C# and relational databases. This allows developers to interact with the database using objects in their code rather than writing raw SQL. ORMs provide a bridge between your code and the database, automatically handling the translation between objects in your code and records in the database table. Now that we understand ORMs, let's explore Entity Framework Core, or EF Core, a widely used tool in the .NET ecosystem. EF Core is an open-source object-relational mapping tool that enables developers to interact with the relational databases using C# objects instead of SQL queries. It's known for its flexibility and efficiency, streamlining database interactions for developers working with C#. For example, say you want to create a new book object called Book2 with the values Charlotte's Web for the title, E.B. White for the author, and 1952 for publication year. EF Core automatically saves it to the database. The same applies to retrieving data. EF Core handles the behind-the-scenes SQL and returns the results as an object in your code. Let's explore some of the key features offered by EF Core, starting with Language Integrated Queries. Language Integrated Queries, or LINQ, allows developers to write database queries directly in C#, making them type-safe, more readable, and integrated into the application's logic. Additionally, automatic database migrations allow developers to evolve their database, like adding tables or modifying existing ones as their application grows. And lastly, EF Core's change tracking feature automatically tracks changes made to objects during their lifecycle, simplifying the process of updating the database with these changes when needed. The use of EF Core enables a number of advantages, like ease of use. EF Core makes working with databases easier because you don't need to write complex SQL queries. You just work with objects in C#. This reduces the amount of code you need to write and maintain. Another advantage is maintainability. Since the SQL is generated by EF Core, you don't have to worry about small mistakes in your SQL code. It handles that for you. Finally, EF Core is flexible. It supports different types of databases like SQL Server, PostgreSQL, and SQLite, meaning you can use the same ORM framework regardless of which relational database is being used. In this video, you learned about the concept of object-relational mapping and the role of EF Core as an ORM tool. Incorporating ORM and EF Core in your work as a back-end developer saves time, reduces complexity, and helps make your code more maintainable. Imagine a project that requires a massive amount of data, and you need a way to organize it so that it's easy to search, update, and analyze. That's where relational databases come in. They provide a logical, efficient system for managing all kinds of information. In this video, we will describe the basic structure of relational databases, including tables, rows, and columns. Relational databases are among the most common databases programmers work with because they offer a structured, organized approach to data management. Relational databases are comprised of a few basic elements: tables, rows, and columns. Let's begin by exploring what tables are. A database table is a structured collection of data organized into rows and columns. Tables are the building blocks of relational databases. For instance, a company might have one table for employees, another for departments, and a third for projects. Each table contains information about its respective topic. Let's now explore how data is organized within tables using columns and rows. Columns represent data within a table that stores specific attributes of the data set. For example, in an employees table, we might have columns for employee ID, first name, department ID, and salary. Each column stores the same type of data. For example, a column containing employee salaries will only have numbers, while an employee's first name column will only have letters and no numbers. Rows differ from columns in that they are individual entries in a table that contains a record of data across all the columns. For example, a row in the employees table might include an employee ID of 001, first name John, department ID marketing, and project summer campaign. Each row is a complete record of one employee. Next, let's explore a way to manage and connect different tables to each other. This is where schemas come in. A schema is a blueprint for the database that defines the structure of the tables and how they relate to one another. Schemas help ensure consistency and organization. For example, the schema defines the columns in each table. It also defines how data in one table, like employees, can connect to data in another table, like departments. To connect tables using a schema, we use primary and foreign keys. Let's start by examining primary keys. A primary key is a special column, or sometimes a combination of columns in a table, that uniquely identifies each row and guarantees that no two rows have the same value for that key. For example, in the employees table, the employee ID would be the primary key. This is labeled in the table as PK. Each employee has a unique ID, making it easy to identify them. Therefore, we can use employee ID as the primary key. Now, let's move on to foreign keys, which help connect tables to each other. A foreign key is a column that creates a link between two tables by referencing the primary key of another table. For example, the employees table has a department ID column, which is a foreign key linking each employee ID to a department in the departments table. This is labeled as FK in our tables. The department ID column is also the primary key for the departments table. Primary and foreign keys work together to enforce relationships between tables. They not only help organize data, but also ensure that the connections between tables remain accurate and consistent. By maintaining data integrity and preventing duplication, primary and foreign keys allow for efficient data management and retrieval across the relational database. In this video, you learned about the basic structure of relational databases, including tables, rows, and columns. Understanding the structure is a fundamental building block of backend development using relational databases. Have you ever wondered how large databases stay organized and efficient even as they grow in size and complexity? Understanding the principles behind relational database design is the key to creating systems that are scalable and maintainable. In this video, we will explain the core principles of relational database design. Relational database design includes three core principles: relationships, normalization, and constraints. Let's begin by examining relationships and how these can help connect different tables within a database. Relationships define how different tables in a database connect to each other. There are three common types: one-to-one, one-to-many, and many-to-many. Let's explore each of these in more detail. A one-to-one relationship means that each record in one table corresponds to exactly one record in another. For example, if we kept track of special edition copies of books, where each special edition is unique to a specific book, we might have a table named Special Editions. Each book table record would have one matching record in the Special Editions table, making it a one-to-one relationship. A one-to-many relationship is more common. One author can write many books, but each book typically only has one primary author. In this case, the authors table and books table are linked in a one-to-many relationship, connected by a foreign key, author ID. This helps us store each author's details once and reference them across multiple books. In a many-to-many relationship, multiple records in one table are related to multiple records in another. In our book database, many books can be written by many authors, and many authors can write multiple books. To represent this, we create a third table, often called a junction table, like book authors. A junction table is a database table that is used to represent a many-to-many relationship between two or more other tables. This junction table is named authors books so that it is clear what tables are joined. Authors books links the books and authors tables. Each record in the books authors table represents one author's contribution to one book, making it possible to track which authors wrote which books. Now that we understand how relationships connect tables, let's explore the principles of normalization in relational database design. Normalization is the process of organizing data into tables, columns, and relationships to minimize redundancy and improve data integrity. In database design, we typically follow three main stages of normalization, referred to as normal forms. The first normal form, or 1NF, requires that each column in a table contains atomic indivisible values, meaning no repeated data within the same field. Let's explore how normalization works in a book database. With first normal form, instead of storing multiple authors in a single field of a books table, we would only store one author per row. The second normal form, or 2NF, eliminates partial dependencies, ensuring that non-primary key attributes are fully dependent on the primary key. To achieve 2NF in our book database, we would create a separate authors table and move the author's name to that. Then we would use a foreign key, such as author ID, to link the books to the authors table. Finally, the third normal form, or 3NF, further reduces redundancy by ensuring that every piece of information in a table depends on only the primary key. This prevents storing details that don't directly relate to the table's main subject. For example, suppose we store additional information about the author, such as their biography or date of birth, in the books table. We would move these details to the authors table. This way, all author-specific information is stored in the authors table, and only the author ID is kept in the books table, ensuring there are no transitive dependencies between non-key attributes. In other words, this ensures a clear separation of information and avoids redundancy. With the data now organized efficiently through relationships and normalization, we need to ensure its accuracy by enforcing constraints. Constraints are rules applied to data to ensure that it remains accurate and follows specific guidelines. Let's explore the most common types of constraints, starting with not null. The not null constraint ensures that certain fields cannot be left empty. In our book database, applying a not null constraint to the ISBN column ensures that no book can be added without a valid ISBN. A unique constraint ensures that all values in a specific column are different. In our book database, the unique constraint ensures that no two books share the same ISBN. The check constraint enforces a rule that data in a column must meet certain conditions. For instance, we could use a check constraint to ensure that the year of the publication for books is always greater than 1500. This guarantees that no invalid years are entered into the database. The default constraint is used to assign a default value to a column if no value is specified. For example, a book's price is not provided. We could use a default constraint to automatically set the price to $10, ensuring there is always a value in that price column. These constraints help maintain data integrity, ensuring that the data is reliable and follows our defined rules. By enforcing constraints, we prevent incorrect or incomplete data from entering our database, keeping everything consistent and valid. The principles of relational database design, relationships, normalization, and constraints ensure efficient data storage, reduced redundancy, and maintain accuracy. Understanding these concepts enables you to create scalable databases that stay organized and maintain data integrity as they grow. Choosing the right database management system, or DBMS, can shape the success of your project. The ability to manage data effectively will influence your application's performance and long-term scalability and maintainability. In this video, we will explain the factors to consider when choosing a DBMS for relational database setup. First, let's clarify what a DBMS is. A database management system, or DBMS, is a software tool that manages, stores, retrieves, and organizes data in a structured way. When it comes to relational databases, there are several well-known DBMS options available. Some of the most commonly used ones are SQL Server, MySQL, PostgreSQL, and Oracle. SQL Server is a powerful database management system developed by Microsoft, often used for enterprise-level applications. It integrates seamlessly with .NET applications, making it a popular choice for developers working in the .NET ecosystem. Conversely, MySQL is an open-source DBMS that is free to use and widely supported. MySQL is known for its reliability and is often chosen for web applications. Another open-source database management system, PostgreSQL, is known for its advanced features and ability to handle complex queries. It's highly customizable and considered more versatile than some other options. Finally, Oracle DBMS is commonly used in large organizations due to its performance and scalability. It offers a wide range of features, but often requires specialized knowledge for effective use. These are just a few of the DBMS options available, but they are some of the most widely popular and widely supported. Before we explore the technical comparisons, let's consider how to narrow down the best option for your project. Developers consider several important factors when selecting a database management system. One of the first things a developer must consider is whether to choose an open-source DBMS or a commercial enterprise-level system. Open-source systems are free and have large communities, making them suitable for smaller projects or startups. Open-source database management systems include MySQL and PostgreSQL. Enterprise-level DBMS often come with dedicated support and advanced features, which may be necessary for larger, more complex systems. Commercial enterprise-level systems include SQL Server and Oracle. Another factor is the intended use of the DBMS and the type of application being built. Some applications prioritize fast data access and high availability, while others emphasize security, data integrity, or regulatory compliance. MySQL can be a good fit for fast data access and high availability. However, for applications that need security and reliability, SQL Server and Oracle might be better choices. Beyond the intended use, another critical factor to consider is performance. Performance refers to the DBMS's ability to efficiently process queries and manage large volumes of data. This ensures fast response times and minimal latency, especially in high-demand applications. A high-performance DBMS executes queries quickly, even with large data sets and complex queries. Options like SQL Server or Oracle are optimized for large-scale systems and efficiently handle substantial data loads. Alongside performance, scalability is another important factor. Scalability refers to the DBMS's ability to grow in size and allow more users to access it without slowing down or requiring significant changes. As your database grows and more users access it, the DBMS must handle the increased load without slowing down or requiring significant changes. Scalability is important for applications expected to grow, such as enterprise software or web services. PostgreSQL and Oracle are known for their scalability. These systems can handle growing data and increase traffic while maintaining performance. While scalability ensures a database can grow with additional need, reliable support is equally important as a system becomes more complex. Support refers to the assistance you can access if something goes wrong or when you need help with configurations or adding new features. A database management system with strong support options can help you troubleshoot issues more quickly and reduce downtime. SQL Server and Oracle offer comprehensive paid support. while MySQL and PostgreSQL have large communities that provide support through forums and online resources. The level of support you need may depend on your project's complexity and available internal resources. Finally, it's important to consider the integration within the development ecosystem. Integration refers to how easily the DBMS connects with applications built using a team's development framework, like .NET. Seamless integration allows developers to reduce setup time and avoid common compatibility issues, improving development speed and reducing errors. SQL Server integrates seamlessly with .NET applications, making it a strong choice for developers working within the Microsoft ecosystem. Other DBMS options such as MySQL, PostgreSQL also work with .NET, but may require additional configuration. Selecting the right DBMS is about more than just installing software. It's about shaping the foundation of your application success. Careful consideration of the features, performance, and future needs of your project will guide you towards the best choice. What does it take to transform raw data into a well-structured and functional database? Understanding the process of setting up a relational database is the first step in creating organized, meaningful information systems. In this video, we will demonstrate the initial setup and configuration of a relational database. Once you've selected your database management system, or DBMS, the setup process can be divided into three main phases. Phase 1 involves installing the DBMS, Phase 2, where you configure the system, and Phase 3, where you create your actual database. Let's start by exploring the first phase, installing the DBMS. First, download the DBMS software from the provider's website. Then select the version that fits your operating system, whether it's Windows, Mac OS, or Linux. After downloading, run the installation file to set up the DBMS. This simply includes opening the file and following the prompts to start the process. During installation, you'll be guided through choosing installation directories and components. The default options are usually pre-selected, and it's safe to use them if you're new to the setup. Once installed, verify that the DBMS service is running. Most systems include a tool to manage this, allowing you to start or stop the service as needed for further configuration. After you have installed the DBMS, you need to configure it for use. When configuring the system, you should focus on three key areas, starting with user accounts. Setting up user accounts is a key security measure. The first user account is typically the admin or root user. This user has full control over the database system, so you want to create a strong password for this account. You might also want to create user accounts for other staff who may need access, for example, managers of specific departments. As you set up users, the next important step is configuring two key security settings: roles and permissions, and network level security. Roles and permission settings define who can access the database and what actions they can perform. For example, a project manager needs to access the project details, but not sensitive financial or employee data. Assigning appropriate roles and permissions helps maintain security while allowing users to perform their tasks efficiently. In addition to roles and permissions, you'll need to configure network security. Network security limits database access to the company's internal network or to specific sets of servers, ensuring that only authorized users within the organization can connect. After configuring the security settings of your DBMS, you'll work on the storage options, setting up how and where your database will store data. Most systems let you choose directories or drives where the database files will be saved. You'll also configure how much storage is allocated to your database, which is important if you expect it to grow over time. With your DBMS installed and configured, the last step is creating your first database. When creating a new database, it's important to follow clear and consistent naming conventions. Your database's name should describe its purpose and avoid spaces or special characters. For a company database, you would name it something like Company DB so it's easy to reference later. After naming the database, you'll need to consider its schema. Recall that a schema is a blueprint of how your database is structured. It defines how the tables, relationships, and other elements of the database are organized. For a company database, you would create a schema that includes tables for employees, departments, and projects. The schema will reflect how these pieces of data relate or map to one another. For example, multiple employees can be part of one department, and multiple departments can be involved with multiple projects. The branches between tables can illustrate these relationships. Each department has many projects, and each project might have more than one department. Defining these relationships clearly is important so the data stays organized and accessible. Finally, you'll begin to set up table structures. Recall that relational databases are composed of tables, and each table consists of rows and columns. When setting up our company database, we'll define a table for each category: employees, departments, and projects. Our employees table includes the columns employee ID, first name, and department ID. The departments table includes department ID, department name, and cost center. And the projects table has columns for project ID, project name, and department ID. You've now successfully created a database named Company DB and designed a schema that includes 3 key tables: employees, departments, and projects, and mapped the relationships between them. Employees belong to departments, departments manage projects, and employees can work on multiple projects. Finally, you structured each table with relevant columns like employee ID in the employees table, project ID in the project table, ensuring that your database is organized for efficient data retrieval and management. From naming the database to defining relationships between tables, you've built a complete system that can store, organize, and retrieve data efficiently. In this video, you learned how to set up and configure a relational database. You now have the tools to shape structured data that can help move your project forward. Whether for managing teams or resources, your ability to create a well-structured database is the foundation for effective data management.
In this lab, we're going to use SQL statements to set up and configure a relational database. We're going to use a MySQL database in this case. We're going to set up the development environment, create and modify database tables using SQL commands. We'll define a table structure, including primary keys, constraints, and foreign keys. And then we'll enforce relationships between those tables to ensure integrity between the data in those tables. And then finally, we'll just test its setup using queries. So the first step is to set up the development environment. We need to log into the MySQL shell. So I'm going to do that using the MySQL command. So now I'm in the MySQL shell and I'm ready to start working with the database itself. The first thing I want to do is create the database. And I'm going to use the create database command to do that. We're going to call our database TechCorpDB. So that created the database. You see the query OK. And there's one row affected, which just means that the database has been created. Now I'm going to use the use command to make sure that we're using the right database as we go through the rest of the exercise. So the database has informed me that the database has changed, and now we're ready to continue working with our database. The first thing we want to do is create a table called departments. There's a couple things we're going to do with this table. You'll notice that we have the ID is auto increment, which means it will be created every time a new row is created, and this is going to be our primary key. We want the department name to be unique. The database won't allow users to add a new department name unless it isn't unique, and that field can't be null when data is written to that table. We have our departments table created, and now we're going to create an employees table. We're going to use the same command, create table, and we're going to set some properties on those fields as well. So we have both tables created. The MySQL tells us that both have been created by that query OK message. For the employees table, we have an employee ID, which is an int value that's also auto increment, and that's going to serve as the primary key. Similar with first name to department name, it can't be null and it has to be unique. And then we're also adding department ID as an int, and this will allow us to create a foreign key with the department's table so that we can ensure integrity between the data in those tables. Step 3, we're going to add a column. So here in this exercise, we're going to modify the employees table by using the alter table command. Go ahead and run that. So this added a column last name with the varchar of 50. It also can't be null. So as we work through this exercise, we're going to be able to add data to the table, and now the employees table has a last name. All right, now in step 4, we're going to add a foreign key to our database. And this is going to allow us to associate a field in the employees table with a field in the departments table so that we can ensure integrity between the two tables. We're going to use the alter table again and add a constraint for the department ID to that table. We add the constraint fkey_department, which creates a foreign key on the department ID and references the department ID in the departments table. So now those two keys will be associated, and we can't add a record to the employees table without also including a department ID for the departments table. In step 5, we're going to test the setup. So we're going to query our departments table. So I'm going to use the describe statement just to see what the departments table looks like. And we can see our fields there. It has a department ID and a department name, so that's good. And now we're going to insert some values into our departments table so that it has specific departments that we can reference in our employees table. So I'm going to go ahead and run an insert into command. So we added 3 records. We inserted HR, engineering, and marketing as departments as values into the departments table. Now those are part of the departments table, and each one will have a unique ID 1 through 3. Now we're going to add some records to our employees table so that we can reference them. So we added 6 records into the employees table. Notice we had to include a department ID because that's now a foreign key constraint. So we referenced the department ID, and we're just using values 1, 2, and 3 because we know those are the values that were created when we added the records to the departments table. Now let's test this. Let's make sure that we can see the records from the employees table, and we're going to join on the foreign key in the departments table. Our join statement is joining on the departments table on the employees department ID where the employees department ID equals departments department ID. So that's how we're matching up the two tables using that foreign key on the employees table. And that gives us our first and last name for our employees, and then it's pulling in the department name from the departments table using that foreign key. So that's how we're allowed to get that data from the database. And the output looks like a single table, but we're using that foreign key to do that, to build that relationship between the two. So this is how you can use SQL statements to not only set up, create, and populate a database, but also query and use foreign keys to build some constraints ensuring data integrity.
When building an application's data structure, the goal is to ensure that the database efficiently stores, manages, and retrieves data. The process needed to help make this happen is called data modeling. In this video, we will define the concept of data modeling and its importance in EF Core. Let's begin by defining what data modeling is and why it's important. Data modeling is the process of creating a visual representation of a database system structure. This visual representation helps in understanding, analyzing, and designing databases. It's like designing a blueprint for a database, outlining the structure and organization of data elements. Let's imagine a library database system. It would need to store information about books, authors, and borrowers. A data model lets you define the schema that organizes these entities into tables. In this library database, there needs to be a table for books that includes information like book ID, title, and author ID. Another table for authors that includes author ID and author name. Each has its own set of rows, like title or author name. And another table for book borrowers that includes borrower ID and borrower name. A well-defined data model ensures your application runs efficiently and that your database accurately reflects your organization's needs. Now, let's explore how data modeling functions in Entity Framework Core, also known as EF Core. Let's start by examining entities and their role in structuring your data. An entity is a distinct object in a data model that represents a real-world concept or object. In EF Core, developers can use a C# class to define an entity corresponding to a table in the database, where each property in the class maps to a column. For example, consider a public class named Book. It could include properties like ID for the book's unique identifier and title for its name. Each of these properties directly maps to a column in the book table of your database. Next, let's focus on how your application communicates with the database. For this, we use something called DB context. While entities organize your data, DB context manages the connections and interactions between your application and the database, acting as a bridge between the database and your code. Let's now examine what DB context does in terms of data modeling. First, DB context is responsible for opening and managing connections to the database. It ensures that your application can access the database when needed and that these connections are properly handled. DB context also provides methods for performing data operations. These operations are also referred to as CRUD operations, which stand for creating, reading, updating, and deleting data. They directly manipulate the entities in your model and are reflected in the database. Finally, DB context tracks any changes made to your entities. When an entity is added, modified, or deleted, DB context tracks these changes and determines which database operations need to be performed when you save changes to the database. DB context handles the complexity of database communication, allowing you to work with the entities in C# and automatically transform them into database queries. In this video, you learned about the concept of data modeling and its importance in EF Core. Understanding data modeling can help you efficiently manage your application's data and ensure seamless integration between your application's logic and a database. Entity classes in EF Core are powerful tools. They're the building blocks of working with databases in .NET. In this video, we are going to explain creating and configuring entity classes in EF Core. To illustrate how to create and configure entity classes, we will use an example of building a company database focusing on employee, department, and project entities. Our first step in the process is setting up entity classes. To begin, we need a place to store our entity classes. Inside our project, we'll create a new folder to store the entities. Most developers call this folder Models. This folder will store all of our model classes, representing your EF Core database tables. Once we have the folder ready, we can define our first entity. In the Models folder, create a new C# file called employee.cs. Start by declaring a public class called employee. The employee class will represent the employee table in the database. Marking the class as public allows other parts of the application to access it. Now, let's define the properties of our entity inside the employee class. We'll define properties for employee ID, first name, last name, and hire date. Starting with the first property, we have employee ID. This is an integer or int. We use getSet in curly brackets. This enables us to read and change the employee ID value. Next, we define the employee's first name and last name properties, both of which are of type string. Just like employee ID, the getSet and curly brackets syntax allows us to read and modify these values. Finally, we have the hire date property, which is of type datetime. Again, the getSet and curly brackets syntax lets us access and change the hire date as needed. Each of these properties creates a column in the employee table and allows us to interact with employee data in our application. One benefit of EF Core, particularly when working with properties, is the use of conventions. In EF Core, conventions are a set of rules that make certain configuration changes automatically, saving developers time and effort. For example, EF Core can automatically identify primary keys based on their naming convention. Let's say we want employee ID to be our primary key. By using the naming convention employee, followed immediately with no spaces by ID, EF Core will automatically make employee ID the primary key. How this works is that EF Core naming conventions for a primary key requires that you either name the entity ID or you select an entity name as we did in this example with employee and add ID right after it with no spaces. Other properties like first name, last name, and hire date will automatically map to columns in the table that store the employee's information. Now that the properties are defined, the next step is to set up relationships between entities. Suppose each employee works for a department. To define the relationship between employee and department, we'll add a department ID property with the type int. As with the others, the curly bracket getSet curly bracket syntax allows us to read and modify these values. To define the relationship between an employee and a department, we also need to add a navigation property. A navigation property is a property in an entity that establishes a relationship with another entity, allowing retrieval of related data. In our example, we declare the property by writing public, followed by the type of the related entity, which is department. This means the property will hold a reference to the department entity class. Then the name of the property, which we'll also call department. This creates a one-to-many relationship where each employee belongs to a department, and each department can have many employees. The department ID acts as a foreign key linking the employee table to the department table. The navigation property in the department class allows you to query which employees are associated with a specific department. Now that the relationships are established, let's examine how to configure the behavior of our entities to fit our application's needs. In EF Core, we can configure the behavior of entities using the data annotations or the Fluent API. Data annotations are attributes that you apply directly to your properties to enforce specific rules. These can include explicitly declaring a primary key, making a field required, or limiting the length of a string. Data annotations are placed directly before the property they are affecting. Suppose you want to explicitly declare employee ID as the primary key. You can use key in brackets above employee ID. You may need to add other behaviors like making a field required or limiting the length of a string. For example, you can use required in brackets on first name and last name to ensure that both names are mandatory. You can also use string length 50 in brackets to limit the length of a string property like first name to 50 characters. These annotations help to ensure data integrity without writing extra code. Data annotations are helpful for more straightforward configurations, but for more detailed setups, we use Fluent API. Fluent API is a method in EF Core that configures entity behavior and relationships through code. It offers more flexibility and control than data annotations. Fluent API is a more flexible approach that allows you to configure entity behavior in detail. Instead of using attributes like required in brackets, you write code inside the onModelCreating method to define more complex behaviors for your entities. To do this, you have to first set up an inherited class, in this case HRDBContext from the DBContext class. Next, you'll map the database table to DBContext using dbset. We do this with dbset with the employee type followed by employees to map the employee entity to the employees table. Then we use dbset with the department type followed by departments to map the department entity to the departments table. Then you'll create the onModelCreating method, which exists inside the DBContext class, which is a key part of EF Core. When the application starts, EF Core automatically calls this method to apply any specific rules or configuration you want to enforce in your database. Make the onModelCreating method accessible only within the class using protected, and indicate that it doesn't return any values using void. Finally, you'll use modelBuilder.entity with the employee type to define configurations for the employee table. Then you'll use the entity.property keyword to specify which properties of the entity you want to configure. You use .isRequired to ensure that the field is mandatory, and .hasMax length 50 to set the maximum length for the field to 50 characters. In this video, you learned how to define and configure entity classes in EF Core. mapping properties to table columns, establishing relationships, and using data annotations and Fluent API. As you work on your project, use these techniques to set up your entities efficiently and logically.
In this lab, we're going to do a number of things. We're going to first set up our development environment to work with EF Core. Then we're going to create and configure entity classes, which will represent the database tables. We'll use DB context to manage the database relationships and context. We'll apply migrations to generate the database schema in the database. And then we'll test the database model by inserting in as well as querying data. So in step one, we're simply going to set up the new application, calling it EF Core Model App. It's going to be a console application. And then we're just going to add some dependencies. So we're going to switch to the folder, and then you're going to add the SQLite and Entity Framework core tools to the application so that we can do all the work that we need to do. In step two, we're going to create the entity classes. So the first class I've created here is employee.cs. It's the employee class in the employee.cs file. And you can see we have 6 different properties, starting with employee ID and ending with department. And here you'll want to add all the types into each of the properties that you're going to set. So employee ID, for example, is int. The first name is the second property we're going to add, which is a string. And then the last one is the department property. Now notice this has the department type. The department uses the department class, and we'll have to create that next. And that's what we'll do in the second file, department.cs. We could create our department class, which we reference in the employee class, and that creates a type for that last property there. In the department class, we're also going to reference the employee class as the last property. We're going to create a list of employee objects called employees, and that's how we fill out that class. So now we have our 2 classes, and those are ready to go, and we can move on to configuring the DB context. I have a file here called companycontext.cs where we actually set up that DB context, and here what we're doing is just referencing our 2 different classes, our employee class and our department class. And then we're going to use SQLite, which is a type of database, and we're setting the source to company DB. Now we don't have that database created yet. That's what Entity Framework is going to do for us. But we're going to use the data source equals company DB in our use SQLite method. In step 4, we're going to apply the migrations. So we're going to first use Entity Framework to create the migrations, and then we're going to use the Entity Framework to update the database, which will create that database for us. So first we'll create the migrations using .NET EF migrations. We're going to add and then use the initial create property. All right, so now we have our migrations. You can see there's a migrations folder created, and it has the migrations ready to go. And now we can use that to create the database. And I'm going to use the command database update to do that. So now that that's done, you can see now we have company DB in our folder structure. So using Entity Framework and those migrations, we use the classes to figure out what to create. It created those migrations, and then we use the migrations to update and create the database. And again, that was defined in our model. So that's how Entity Framework knew what to create. We define that here, company.db. So in step 5, we're going to test our database. In program.cs, I've created a couple of things here. We're going to create a new department. The name of the department is going to be engineering, and we're going to add a couple of employees to that department. And then we use the database context to save changes, and then we're going to write out to the console how many employees we actually have in our database. We're going to fill the employees variable using that database context again and running a query against the database to get the number of employees, and we'll use employees.count to return that to the console. So I'm going to run this application, and you can see there we have employees, and engineering is now 2. We added those 2 employees to our database We queried the database and got the count back. So using EF Core and C# classes, you can create some powerful code that can manage a lot of your database operations for you.
CRUD operations stand for create, read, update, and delete. And it's these operations on data that are the foundation of any interaction with a database. In this video, we'll explain the basic CRUD operations and their implementation in EF Core. Let's start by exploring the components of DB Context, because DB Context provides the tools to perform CRUD operations efficiently. Along with methods, you'll use DB Context core components of DB set and save changes when implementing CRUD operations. A DB set represents a table in your database. Each entity class, like employee, is mapped to a specific DB set, which acts as a collection of entities that you can query, add, update, or delete. For example, DB set with the type employee represents the employees table, and it enables CRUD operations on employees. Save changes commits the changes made in the DB context to the database. Whether you're adding, updating, or deleting, calling save changes finalizes the operation and saves your modifications. Without this method, your operations won't be reflected in the actual database. Now that we've described these two core components of DB context, let's explore how to manage data effectively using CRUD methods. First, let's review what CRUD stands for. CRUD stands for create, read, update, and delete. These are the four basic operations you can perform on data in a database. Now, let's go into more detail about what each operation does and how to implement it in EF Core. Create is an operation that allows you to add new records to your database. In DB context, you can use the add method to create new records. To add new data, you first create a new instance of an entity and populate its properties. Then you add it to the DB set using the add method. Finally, call save changes to persist the new record in the database. This method allows you to add a new record, like an employee, to an entity in the database. Next, the read operation lets you retrieve existing data from your database. This is commonly done through querying the data to display it or process it further. To retrieve data from the database, you can use methods like find to get a single record, first or default to retrieve the first matching record, or to list to retrieve multiple records to query the DB set. These methods help you perform the read operation by querying the data stored in the database. Another CRUD operation is update. Update lets you modify existing records. When something changes, you perform an update to reflect the new information in your database. In DB context, the update method is used to modify existing records. When updating data, first retrieve the entity from the DB set using the find or toList method, then modify its properties and call save changes. EF Core tracks these changes, and when you save them, the entity is updated in the database. Finally, delete is the CRUD operation used to remove records from your database. Once a record is no longer needed, you can delete it to free up space or clean up your data. In DB context, deleting an entity involves retrieving the record you want to remove using the find or toList method, passing it to the remove method, and calling save changes as we discussed earlier. The remove method allows you to delete an entity from the database. Once the entity is marked for deletion, it is removed when changes are saved. In this video, you learned about the basic CRUD operations and their implementation in EF Core. By mastering these essential operations in EF Core, you unlock the potential to manage data in any application.
In this lab, I'm going to use EF Core to create a database context and then implement CRUD operations to read from and write to a database. So in step one, you're setting up your environment. You're going to create a new console application product management app, and then just add some .NET packages to enable EF Core in the application. Now in step 2, we're going to define the data model for our application. We already have the database installed and populated, so we don't need to do that. So we're going to just essentially create the model for the product itself that will read to and write from the database. When we get data from the database, we need somewhere to store it. So this product class will allow us to store that data. And you can see the product class here. It's just got 3 properties: ID, name, and price. And this is what we'll use to interact with the database. In step 3, we're going to set up the database context. I'm going to go to my application dbcontext.cs file. Here what we're doing is using MySQL. I'm using the options builder class, and we're going to set the server information so that EF Core knows how to talk to the database. We're using a database called ProductDB, set a username and password there, and we're just setting the SQL version for that. So you can also see here we're setting up a dbset class using the products class that we created earlier. And this just allows us to write to and from that products class as we talked about earlier. Notice too here we're using DB Context Options Builder. That's the class that we want to use to create that Options Builder instance. And so we can actually use MySQL when we're writing to and reading from the database. In step 4, we're going to apply the migration. So here's where we actually start to use EF Core to interact with the database. And in order to apply those migrations, we're going to use a .NET command and calling the EF application to do that. So I'm going to actually run those in the terminal. And we're going to use we're going to call .NET EF, which uses the Entity Framework application. I'm going to call the migration. We're going to use the migrations flag. We're going to add an initial migration to our database. When I run this, you'll see that it will show up, but there's going to be a migrations folder that will appear, and we'll have those migrations ready to be able to import into the database. So I'm going to run this command. The migration ran. Entity Framework, we used Entity Framework to create the migrations, and you'll see the migrations now exist in the migrations folder after we run that command. I'm going to run one more command, and that's to update the database using the Entity Framework migrations that we just created. So I'm going to use Entity Framework again, the application, and I'm going to tell it to update the database that we're working with. And it's going to use the database information that we put in that options builder use MySQL statement, so it knows which database to interact with. Okay, so the database update ran, and now in our database we'll have that products table, and we can use that to interact with data. So in the next step, step 5, we're going to implement our CRUD operations. And to do this, I'm going to go over to program.cs. And you'll see that we have different operations here: create, read, update, and delete. So those are our 4 operations that we can perform against the database. In this instance, I'm going to run this. When the application runs, it's actually going to write data to the database and then output to the console to show us that it actually interacted with the database based on the migrations that we just built. So I'll go ahead and run this application, and you'll see in the console that it actually did update the database. Before we do that, I'm going to just walk through a couple of these items. So you'll see under laptop price, I'm just going to put a price in here. It's just going to be a number that will be used when we create the product. And then for all the contexts, we're going to use the context.savechanges method, which will force the changes to the database once we've made those changes. That's the command, the method that we'll use to commit those changes, regardless of what the operation is. So I'm going to run this application. And you can see now it has products in the database. The product is laptop, and the price is $999.99. And we can see that here. That's what we did when we ran the application to add that new product to the database. So using Entity Framework, we can create a migration, update the database with that migration, and then use CRUD operations to interact with that table that we created using Entity Framework.
Understanding Entity Framework Core and relational databases is essential for efficient data management and system performance. With these skills, you can structure, manage, and optimize data, ensuring your backend systems are scalable and robust. We began by examining Entity Framework Core's key features and functionalities, and its role in managing databases effectively. Next, you explored the fundamentals of relational databases, focusing on their structure, essential principles, and how they form the backbone of efficient data management. Then, you learned how to set up a relational database, covering each essential step required to establish a functional system. After that, you explored data modeling with Entity Framework Core, focusing on efficiently structuring and representing data within the framework. Finally, you applied basic CRUD operations using SQL and aggregate functions to manage and analyze data effectively. Mastering Entity Framework Core and relational databases is important for building robust and scalable back-end systems. By applying these tools and techniques, you'll manage data efficiently, optimize database performance, and enhance the overall functionality of your applications. Welcome to the basics of SQL. In this module, you'll explore SQL's core syntax and functionalities, gaining a foundational understanding of how this language drives database management. From retrieving data to manipulating and combining it, you'll develop the skills to interact with databases efficiently and effectively. We will begin by defining SQL's basic syntax and functionalities, and understanding how this foundational language operates within databases. Next, you will explore how to retrieve data using select statements, learning to query databases efficiently and extract the information you need. Then, you will learn how to manipulate data using insert, update, and delete statements, mastering the tools to modify and manage data effectively in SQL. After that, you will focus on combining data from multiple tables using SQL join clauses, learning how to build complex queries that integrate data seamlessly. And finally, we will work with SQL to aggregate functions, learning to perform advanced calculations and data transformations for deeper insights. By the end of this module, you will have the skills to write and execute SQL statements with confidence, from retrieving data to combining tables and performing complex calculations. Let's get started with mastering the basics of SQL. Structured Query Language, or SQL, is the key to unlocking the full potential of relational databases. While tools like Entity Framework Core reduce the need to write raw SQL by allowing you to interact with databases through C# code, understanding SQL remains important for direct database management and handling more complex scenarios. In this video, we will define the basic structure and syntax of SQL queries. Structured Query Language, or SQL, is a computer language used to communicate with and manage relational databases. SQL provides a way to interact with and manipulate data stored in a relational database system. More specifically, it enables users to query, insert, update, and delete data within a database. At the core, SQL is a query. A query is a request made to a database to retrieve, insert, update, or delete data. Let's imagine we want to retrieve information about books in a library database. A query will include instructions to select specific details from a table of books, such as a title or author, and possibly apply conditions, like only showing books published after 2020. Now, let's explore SQL queries in more detail, starting with how they're structured. The structure of SQL queries includes keywords, clauses, and expressions. First, keywords are reserved words in SQL that perform specific functions, like selecting data from a table or inserting new information. These might also be referred to as statements or commands. For example, when we want to retrieve book titles, we use the keyword select to tell the database we want specific information. So our query would start with select book title. Next, clauses are part of the query that specify operations or conditions. They help filter the data or identify which tables the query interacts with. In our library example, if we only want results from a particular table, like the table named books, we would use the from clause to specify this condition. Building on our query, we would add from books after our select statement. Expressions are the final part of our query structure. Expressions are combinations of values, operators, and functions that evaluate to a single value. These are often used to apply conditions or perform calculations. For example, in our library, we might use the where clause and include an expression to find books published after 2020. To add this expression to the query we've been building, we use a where clause and include an expression asking the query to only return results if the publication year is greater than or equal to the year 2020. We do this using greater than and equal to sign operators to compare publication year and 2020. Now, let's explore some of the most commonly used SQL keywords or commands. These commands represent core operations you'll perform frequently when managing databases. Select retrieves data from a table. In our example, this command would retrieve information about specific books, like titles or authors, from the library database. Next, the keyword insert into adds new data to a table. For example, if the library purchases a new book, we would use insert into to add book title, author, and publication year into the books table. Then the update keyword is used to modify existing data in a table. If a book's details need to be updated, you would start with this command to modify the relevant data. Another important SQL keyword is delete. The delete keyword is used to remove data from a table. If a book is no longer available in the library, this command would delete its record from the database. Along with these keywords, the where clause specifies a condition that filters which rows should be affected or returned by the query. If, for example, we want our query to return only books by a certain author, the where clause will apply that condition. In this video, you learned about the basic structure and syntax of SQL queries, including the use of some common SQL keywords and the where clause. Even if you rely on tools like EF Core to handle most of your database interactions, understanding the structure and syntax of SQL queries will help you manage data more effectively and work on advanced scenarios. Databases are at the heart of almost every modern application. Understanding how to interact with them is crucial for managing and retrieving data efficiently. Whether it's viewing records, updating them, or even adding new data, SQL provides powerful tools for performing these tasks. In this video, we will describe the functionalities of core SQL commands. You already have a basic understanding of SQL's core commands: select, insert into, update, and delete. Now, let's take this knowledge further and examine how these commands function in different situations to manage and manipulate data effectively. Let's start by examining how the select command is used for retrieving data. The select command retrieves specific data from a table based on the column or conditions you define. Suppose you're working with an employee database. First, you need to select all the data in a table. You can retrieve everything, every row, and every column using select. Next, let's narrow it down. Maybe you don't need all the columns, just certain ones. Imagine you want a list of employees who are part of the marketing department. Here, you would use select with where to filter the data by department. Finally, you can also use the select command for complex queries, like specifying the number of records to retrieve. Imagine you want to retrieve the top 5 highest paid employees from the employees table. You can use select top to limit the number of rows returned. This is useful when you're only interested in the first few results based on specific criteria, like salary. For example, select top 5 would return only the first 5 rows, typically sorted by salary if combined with an order by clause. This is helpful for generating quick summaries without processing the entire data set. What if you want to do more than retrieve data from a table? What if you want to add data? Well, this is where the insert into command comes in. Insert into enables the adding of new data to a table. Suppose a new employee starts at your company, and you need to add one new record to the database for them. You can use insert into to add a new row of data into a table by specifying the columns and values. Another scenario could be that a new group of interns all starts at the company at the same day. You can also use insert into to add multiple records. Finally, say that you actually have a separate interns table and you want to copy the new interns records from the employees table to the interns table. You can use a combination of insert into and select commands to copy records from one table to another table. Now, what if you need to update data that already exists in your table? You can use the update command to modify existing data in a table. As with the other commands, you can use the update command to change a single record or even multiple records if needed. For example, you can use the update command to change the salary of one or more employees. You can also update a record based on a subquery in the clause using data from another table. This is especially useful when the data you need to update depends on information stored elsewhere in your database. For example, imagine you want to update an employee's department in the employees table, but you need to pull that department information from a separate departments table. By using a subquery, you can update the department in the employees table based on matching a department's ID from the departments table. Finally, the delete keyword removes data from a table. Similar to the update command, you can use the delete command to delete one record, multiple records, or delete a record based on a subquery. You can also delete all of the records in a table. Developers rarely use the delete command for this purpose, as it cannot be undone. It's also important to note that deleting all the records in a table does not delete the table. It maintains the structure and schema of a table. To delete a table, you can use the drop command. In this video, you learned about the functionalities of core SQL commands. By mastering these core SQL commands, you'll be equipped to handle most data management tasks effectively, whether you're retrieving, inserting, updating, or deleting data. SQL provides a powerful toolkit for maintaining and optimizing your database systems. Practice these commands to become confident in managing any relational database. Data is one of the most valuable resources in the modern world, but knowing how to ask the right questions to retrieve the information you need is even more important. SQL select statements allow you to ask those questions and retrieve data from a database. In this video, we'll write simple select statements to retrieve data from a database. Let's begin by reviewing the basic syntax of the select statement. This is the foundation for retrieving data from a database. The basic syntax starts with the keyword select, followed by the column name, or names if there are multiple, then the keyword from, followed by the table name. Select tells the database you want to get data. Column 1 and column 2 are the specific columns you want to retrieve, and from table name specifies which table to get the data from. Now that you understand the basic syntax, let's start with a simple query that retrieves only specific columns. Suppose you want to get results with only the first and last names of employees from an employees table. You would write the query select first name, last name from employees. This retrieves the first name and last name columns from the employees table. Next, let's explore some other scenarios and how to write the queries. For example, you might want to retrieve all the data from a table. To do this, you use an asterisk to select everything. To get all the columns and rows in the employees table, you would write the query select asterisk from employees. Now, let's consider how to retrieve data with no duplicates. If you want to retrieve only the unique values and remove duplicates, you can use select distinct. For example, suppose you want to get a list of unique departments. You would write select distinct department from employees. This query returns each department only once, even if multiple employees are in the same department. What if you only want to retrieve the highest values in your data? For example, writing a query to find the highest salaries. You can use select top to limit the number of rows returned based on a condition. To retrieve the top 5 highest salaries in the employees table, you would write select top 5 from employees, order by salary DESC. This limits the result to the 5 employees with the highest salary, sorting the results in descending order based on salary. It's useful when you need to focus on key data points, like the highest earners in an organization. In this video, you learned how to write simple select statements to retrieve data from a database. The ability to ask the right questions in SQL can transform how you interact with data, unlocking the insights hidden within it. Practice these basic select statements and you'll soon be able to retrieve exactly the data you need whenever you need it. In SQL, being able to filter and sort your data helps you get the exact information you want. Whether you're narrowing down thousands of rows or sorting your results to focus on key insights, mastering the where clause and order by clause is key to making sense of your data. In this video, we'll use the where clause and order by to filter and sort data in SQL queries. Let's start by explaining the where clause. The where clause in SQL is used to filter records by specifying conditions that must be met for rows to be included in the query's results set. The where clause is used within SQL statements like select to filter rows based on specific conditions. The basic syntax for a select statement using the where clause would be written starting with the keyword select, followed by the needed column names. Next, we use the keyword from and then the table name. Finally, the where keyword is used, followed by the condition you want to imply. For example, you can specify that only certain rows should be returned based on comparison operators like equals, greater than, or less than. You can even combine conditions using logical operators like and or to make filtering more precise. This way, you can make sure you're retrieving exactly the data you're interested in. Suppose you want to write a query that returns only the employees from the HR department. You'd write the query like this. Start with a select statement listing the columns we want to return from our query, first name and last name. Then use from employees to tell the query we want it to search the employees table for the data. Now, add a where clause to request only those employees within the HR department. We do this using an equal sign operator setting department equal to HR. Once you've applied a basic filter like the one from our last example, you might want to narrow your results even more. For example, if you're interested in only those employees from the HR department who earn more than $50,000, you can do this by combining conditions using the AND operator, which lets you get even more specific with your queries. Let's start with a query we've been building. To have the query also filter the results by employees with salaries greater than $50,000, let's add the AND operator to the end of the where clause like this, and salary greater than $50,000. This query will now return the first and last names of all employees in the HR department with salaries greater than $50,000. Note that using the AND operator means that both conditions need to be true. Like in our example, an employee would need to be in the HR department and have a salary greater than $50,000. Let's now make things a bit more complex by adding a different condition to the where clause, this time using the OR operator. Suppose you want to query for employees who are either in the HR or finance departments and who have more than 5 years of experience. For this, we need multiple conditions. Let's start with a select statement. Select first name, last name, and department from the employees table. Then, let's use a where clause to further define the results we want from our query. We start by using the OR operator. In parentheses, we set department equal to HR or department equal to finance. By using OR, we're saying that either can be true in our results. An employee can be part of the HR department or the finance department. To further filter our results to employees who have more than 5 years experience, we use the AND operator and then set years experience to greater than 5. This query will return results that include first name, last name, and department from the employees table for those employees in either the HR or finance departments and who have more than 5 years of experience. Now that we've learned how to focus on just the data that matters by filtering, the next step is organizing that data to make it even more useful. We do this by using the order by clause. The order by clause in SQL sorts a query's results set by one or more columns in ascending or descending order. To use the order by clause in a select statement to sort the query results by ascending order, the basic syntax is to add the order by keyword to the end of the query with the column name. ASC is added to tell the query to sort by ascending order. The order by sorts in ascending order by default, so it's not required to include it. However, if you want the order to be descending, you'll need to include DESC. Let's illustrate using a simple example. Say you want to find all the employees sorted by last name in ascending order. We could write the query using a select statement that includes the first name and last name from the employees table and finish with order by, followed by the column last name and then ASC. Again, order by uses ascending order by default, so adding the ASC is not strictly needed. This query will return a list of employees' first and last names from the employees table sorted by last name and arranged alphabetically in ascending order. Now that you've learned how to filter in a SQL query using the where clause and sort using order by, let's combine filtering and sorting for a more advanced query. In this example, we want to query for employees from the HR department and sort them by their salary with the highest earner at the top. Let's start by selecting first name, last name, and salary from the employees table. Then let's use a where clause to set department equal to HR. We will add our order by keyword, then salary, and finish with DESC. This query will return first and last names and salaries for employees in the HR department, and the results will be sorted in descending order from the highest salaries in the results to the lowest. In this video, you learned how to use where clauses and order by to filter and sort data in SQL queries. Experiment with different filters and sorting techniques to figure out how they change your data retrieval results.
In this lab, we're going to be using SQL statements to interact with a MySQL database. On my computer, I have a MySQL database called SampleDB, and it has a single table called employees with some sample data in it. And we're going to write individual SQL statements to interact with that table. So in step one, we're going to use a select statement to select all the records out of the employees table. And I'm going to use the star, which tells SQL to retrieve all the records from the table. So you can see that the records were retrieved. There's a first name, last name, and department, salary, and years experience columns. And here's all the records in that database. Now in step two, we're going to retrieve specific columns from the database. So let's suppose we just want the first and last name from employees. We can use another select statement. And in this case, we're going to specify the columns that we want to use. So I'm going to use this command, select first name, comma, last name. And if we wanted to select department, we can use comma department. But for this exercise, we're just going to use first name and last name. And when I run that, it should just provide the first name and last name columns from the table. Step three, we're going to filter our select statement and just get specific rows back. We just want those records that only where the department is HR. For this statement, we're going to use the where clause, and the where clause will restrict what SQL Server will return from the table. So you can see here I'm saying I want to specify the department as HR, and the where clause is how I do that. So there's two records that are returned. It returns all the columns, but only those records that have HR as the department. In step four, I'm going to use the order by clause, and this allows us to sort the returned values. And in this case, I'm going to sort by salary, and I want to sort the salaries in descending order. So this should give us the highest salary first and the lowest salary at the bottom using that order by clause. And you can see here we have at the very top the highest salary of $95,000 and the lowest salary of $42,000 at the bottom. Step five, we're going to combine where and order by, and we're going to select the records where the department is engineering, and we're going to again sort by years of experience this time, and we're going to sort those in descending order. So we have department where department equals engineering, and so that's how we're joining these two ideas. Years experience is greater than 3, so now we have a compound where clause. So we only want people that are in engineering that have years of experience that are greater than 3, and we're going to order by the years of experience in descending order. So we get 3 records back. You can see the salaries are ordered from highest to lowest, and all the years of experience show greater than 3. Now, using SQL, we can also aggregate and group data right in the command. We don't have to have that data in the table. We can do it in the select statement itself. So the first operation I'm going to do is get all the total salaries by department. What I've asked SQL to do here is to select the department and then sum the salaries as the total salary from the employees table and group by department. So the output that it gave me is each department and how much the total salaries are for that department. So you can imagine a scenario where you need to see how much your spend is based on each department and which department is costing the most, which is the least. This query does that very easily and very quickly. The next thing I'm going to do is count the number of employees in each department. And so instead of using sum, I'm just going to use this command, the count keyword. You can see the return here. It selects from the department. It counts using star, so it's going to count all the employees as employee count. And what that did is created a new column in my output from the employees table, and I'm going to group them by department. So we can see engineering has 3 employees, human resources has 1, we have a finance that has 2. So you can see that the output will provide that count for us and actually create a new column for us as we look at the data in the database. So using SQL statements, you can interact with your database. We're only showing select statements here, so we're only getting data from the database. But you can also do other operations where you can write data to the database, delete records, and so on using SQL statements.
When working on a live database, adding new information quickly and accurately is essential. Whether managing user data, product inventories, or transaction records, knowing how to insert new records smoothly is a key skill. In this video, we'll explain how to insert new records into a database using insert statements. The insert statement is a SQL command used to add new rows to a table in a database. It's a foundational tool in data management, allowing applications to store new information and helping organizations keep their data current and organized. The insert statement specifies the table and columns where data will be added, followed by the values to be inserted. The basic syntax begins with insert into, followed by the name of the table to which you're adding data records to. Next, you specify the columns in which you'll be inserting values. After that, you use the keyword values and provide the actual data that you want to insert. Each value corresponds to the column in the same order. Let's begin with an example of inserting a single row. Suppose we have a table called customers. We would use an insert statement to add a new customer named John Doe with a customer ID of 1. This statement starts with insert into, followed by the name of the table we're adding data to, in this example, customers. After that, we list the column names first name, last name, and customer ID, all enclosed in parentheses. Next comes the keyword values, followed by the actual data we want to insert. John for first name, Doe for last name, and the number 1 for customer ID, again enclosed in parentheses. Notice that text values are placed inside single quotes, while numbers stand alone without quotes. This approach allows us to insert a single record into the table. What about adding multiple rows at once? Instead of using multiple insert statements, SQL allows you to add multiple rows in one statement, which can significantly improve performance. The process for inserting multiple rows is similar to inserting a single row, but instead of providing one set of values, we include multiple sets, separated by commas. Let's break down the example for inserting 2 customers, Jane Smith and Mike Brown. The statement begins with insert into, followed by the table name customers. Next, we list the column names enclosed in parentheses, first name, last name, and customer ID. After that, we use the keyword values, followed by 2 sets of values. Each set is enclosed in parentheses and separated by a comma. For Jane Smith, the values are Jane for first name, Smith for last name, and the number 2 for customer ID. For Mike Brown, the values are Mike for first name, Brown for last name, and the number 3 for customer ID. Notice again that the text values are placed inside single quotes, while the numbers stand alone. This method inserts both rows in one statement, making the operation more efficient than using separate insert statements for each record. Now, let's explore a more complex example. Often, you will need to insert data into a table with foreign keys, where the data must align with foreign key constraints. To illustrate, let's use an example that involves foreign keys. In this example, we're inserting data into an orders table, which has a customer ID column, acting as a foreign key, meaning it links to the customer's table. To insert a new order, the customer ID in the orders table must correspond to the existing customer in the customers table. For instance, if we know that customer ID 1 refers to John Doe, we can insert an order for him. The insert statement begins with insert into, followed by the table name, orders. Next, we list the column names, order ID, customer ID, product, and quantity, all enclosed in parentheses. After the values keyword, we provide the values we want to insert. The order ID, 102, the customer ID for John Doe, which is 1, the product being ordered, in this case smartphone, and the quantity, which is 3. The foreign key constraint ensures that the customer ID we're referencing must already exist in the customer's table before the new order can be added. If we attempt to insert an order with a customer ID that does not exist in the customer's table, the database will return an error, preventing the operation. This error serves as a safeguard to avoid records with missing or incorrect relationships between tables, ensuring that every order has a valid customer reference. In this video, you learned how to insert new records into a database using insert statements. Whether you're adding one record or many, the insert statement makes it easy to add new data to your database. Practice these examples, and soon you'll be comfortable with adding data to any table. Imagine you're managing a large customer database, and you discover an error in multiple records, or perhaps some data is outdated and needs to be removed. How do you make these changes safely without disrupting the entire system? SQL's update and delete statements provide a reliable way to modify existing records and remove data. By using these statements with specific conditions, records can be accurately targeted, reducing the risk of unintended changes. In this video, we will demonstrate how to update existing records and delete records using update and delete statements. Let's begin by defining what the update statement does. The SQL update statement modifies existing records in a database table. The update statement is used to change data within one or more columns of a database table. In backend development, it's frequently used to keep data current without replacing the entire record. Let's now explore the syntax used for the update statement. The syntax starts with the keyword update, followed by a table name, and then the set clause, which specifies the column and the new value. Finally, a where clause is added to target the specific record you want to update. Without the where clause, all records in the table would be updated, which is usually not the desired outcome. Now, let's explore an example of how to use the update statement to modify a specific record in a table. Suppose you need to update the genre of a particular song in a music catalog. For example, if the song Hey Jude was mislabeled and you need to change its genre to rock, you would use an update statement. This statement begins with update, followed by the table name, in this case, music catalog. After that, we use set, followed by the column we want to update, genre, and assign it the new value of rock. An important part of this statement is the where clause. This clause specifies which records should be updated. In this example, the condition is that the song title must be Hey Jude. The where clause ensures that only the record with that specific title is modified, and no other records are affected. Now that we've explored how to update a specific record using the update statement, what if we need to modify several records at once? Let's examine how to do this by updating multiple records based on a condition. In cases where you want to update multiple records, you use a similar approach, but the condition in the where clause will target more than one record. For example, suppose you want to mark all songs with over 1 million weekly listeners with a popularity of virality. The update statement starts with update followed by the table name music catalog. Next, we use set to specify the column we want to change, popularity, and assign the new value of viral. The where clause here is crucial. It ensures that only the records with a value for weekly listeners that's greater than 1 million are updated. This condition allows us to modify several records that meet this criterion, updating their popularity all at once. With the update statement, we learned how to modify data in a table, but sometimes you may need to remove data entirely. Let's explore what the delete statement does and then how to safely delete records from a table using the delete statement. The delete statement is essential for removing unwanted data while maintaining table structure. This can include outdated records, duplicates, or data that no longer meets business requirements. The syntax starts with delete from followed by the table name. The where clause is then added to specify which data should be deleted. Without the where clause, all data in the table would be removed, so it's important to include this condition to avoid unintended data loss. For example, if you need to delete a song from your catalog, like an outdated or irrelevant song, you can use this delete statement. In this example, the statement starts with delete from, followed by the table name, which is music catalog, and the where clause is added to ensure that only the song title obsolete song is deleted, leaving the rest of the records intact. There may also be cases where you want to delete all records from a table. Let's explore when this might be necessary. Suppose your music catalog is undergoing a complete reorganization, and you need to clear out all the existing data to start fresh with new entries. In this case, you can use a delete statement without a where clause. The statement starts with delete from, followed by the table name, which is music catalog. Since no where clause is provided, all the records in the table will be removed. However, the table structure itself will remain intact, allowing for new data to be added later. This approach is useful during system resets or when you need to replace the entire dataset. Whether you're updating or deleting data, ensuring the safety of your database is crucial. So let's go over some essential safety practices to prevent accidental data loss. Whenever you use update or delete statements, it's crucial to include a where clause to target specific records. Failing to do so can result in widespread modifications or deletions, which could compromise your data. Additionally, it's good practice to run a select query first with the same where condition to verify that the correct records will be affected before executing the update or delete statement. In this video, you learned how to update existing records and delete records using update and delete statements. You also learned some safety practices to avoid unintended updating or deleting of data. With these practices in place, you'll ensure your database remains accurate and reliable, supporting smooth operations across your entire system.
In this lab, we're using SQL query language to do inserts, updates, and delete operations on data. And we're going to be able to add new records, modify records, remove some records from the table, and look at some safety techniques that will prevent us from removing or deleting data that we don't want to delete. So in step one, the first thing we're going to do is create the table users. I have employees DB database. It has no tables in it yet, so we're going to, first step is we're going to create that table users. And we'll use the create table command, and we'll create a table that has some fields: user ID, first name, last name, email, and age, each with its own data type. So now that we have the table created, we can start to add data and manipulate it. Notice that for each of these fields, we're adding the specific fields that we want to work with. These could be anything depending on the data that you're working with. Here, we're just picked ones that are related to user type of data. In step two, we're going to add data into the table, and this is where we use our insert feature. insert function. So using insert, you can actually populate data manually like we're doing in here, or you can read it in from a file. Here we're just adding 3 users to our user database. We've got a return value here of query OK, 3 rows affected, which means that the query ran and added those 3 rows to our database. So using insert into, we have to specify the table name, which is users. Then we can tell SQL what fields we're going to add, and then the values specifies what specific data we want to add as well. In step 3, we're going to use the update function to update a specific name. So I'm going to, we're going to update the user whose first name is May, and we're going to set her age to 26. You can imagine a scenario where the data was entered wrong and now you need to update it. So we're going to do that using the update statement. Once we run that command, you can see that it updated 1 row and 1 record was changed. So we're going to set the age equal to 26, and we're going to use the where clause to specify which record we want to update. So the first name here would be May. In a real world scenario, you would probably want to use something like an ID, particularly when you have hundreds or thousands of records. Using a specific ID is usually unique. So it would be more foolproof so that you don't make a mistake. But in this case, we can also use first name because our data set is so small. Now in step 4, we're going to remove a user, Aisha Khan, from the database. To do that, we're going to use the delete from command. And I'm going to use the delete from the users table where the last name equals Khan. It tells me 1 row is affected, so the data was removed. Here we're using our where clause of last name equals Khan. In a real world scenario, you would probably want to use an ID that's unique across users, but because our data set is small, we can just use the last name. In some scenarios, we want to be careful, obviously, before we delete. So we can run a select query first. So we're going to select from the users table every user who has a last name of Garcia. And we want to make sure that if we're going to delete a record, we're deleting the correct record. So here we have one user, Carlos Garcia, is the only record in our database. And we know that we need to remove the record for Carlos Garcia. So now we can safely run the next command that states that we're going to remove the record of the person whose last name is Garcia. Because there is no other Garcias in the database, we're going to get the right record. So when we run that query, it removes the record from the database, and we can select again, and now we see that there's no users whose last name is Garcia. We have an empty set because we removed that data. So using SQL query language, you can perform a lot of operations. These are very basic operations that a database engineer will perform many times a day. These are the standard ways of interacting with data in a MySQL database.
Combining data from multiple sources is often essential in real-world scenarios. But how can you make sense of all the different tables in a database to get the information you need? SQL join clauses provide a powerful way to connect related data. In this video, we will explain the purpose and types of join clauses in SQL. In SQL, join is a clause used to combine rows from 2 or more tables based on a related column between them. This is necessary when data is spread across multiple tables, which is a common practice in relational databases to keep data organized and avoid redundancy. Joins allow you to query data across these related tables in a structured way. Without joins, you'd be limited to accessing just one table's data at a time. Suppose you want to review all orders made by a specific customer. You have a table for customers and another table for orders. A join can help you find which customers made which orders by combining these 2 related data sets. The key here is that the tables must have something in common, like a customer ID in both tables that links the data together. That's where primary and foreign keys come in. The most important link between tables in a join is often a relationship defined by a primary key and a foreign key. A primary key is a unique identifier for each row in a table, Well, a foreign key is a column in another table that refers to the primary key. Joins work by using this relationship to combine data. For example, a customer ID might be the primary key in a customer's table and a foreign key in the orders table. This relationship ensures that the data from both tables corresponds accurately. Without well-defined primary and foreign keys, joins are much harder to execute reliably because the relationship between the tables is unclear. Now that we've established how primary and foreign keys help define relationships between tables, let's explore different types of joins that can combine the data based on these relationships. Each type serves a specific purpose depending on how you want to combine the data and what information you need. The inner join is the most commonly used type of join. It returns only rows where there is a match in both tables. In our customers and orders example, an inner join would return only the customers who have made at least one order, leaving out customers without any orders. This join is useful when you only want to get data where there's a clear connection between the tables. While inner joins give us only the data that matches in both tables, sometimes we need to retrieve all data from one table even if there isn't a match in the other. This is where the left join and right join come in. A left join returns all the rows from the left tables, or the first one in the query, and the matching rows from the right table. If there's no match, the result will still include the rows from the left table, but with null values for the columns from the right table. Suppose you want to retrieve all customers' order history, while also including those who have an account but haven't placed any orders yet. A left join would be the way to go. This would retrieve all customer data and combine it with any related order information. For customers who haven't made any orders, their order details will appear as null, but they'll still be included in the results. Now, the right join works similarly to the left join, but in reverse, returning all rows from the right table and the matching rows from the left table. When there's no match, it fills in the missing left table columns with nulls. You might use a right join to retrieve a list of all orders, including the relevant customer information. If some of the customer information, say a date of birth, is missing, it would return a null value for that data point. Finally, let's explore the most inclusive join type, the full outer join, which returns all rows from both tables whether or not there is a match in either table. If there's no match, the results will still include all rows from both tables with nulls where there's no match. This join is useful when you want a complete view of the data, regardless of whether or not the data is fully linked between the tables. For instance, you could get all customers and all orders, even if some customers haven't placed any orders and some orders aren't tied to any customers. Now that we've covered the different types of joins, let's move on to the syntax used to write join statements in SQL. Join clauses are added to a select statement to specify how tables are related. The basic structure of a join begins with a select statement, where you specify the column or columns you want to retrieve. This is followed by the from clause, where you provide the first table name, often considered the left table in the join. Next, the join keyword is used and then followed by the second table name, referred to as the right table in the join. The query concludes with the on clause, which defines the relationship between the two tables. In the on clause, you explicitly specify how the tables are related by using table1.column equals table2.column. This part of the query tells SQL to match the rows from table 1 and table 2 where the values in these columns are equal. Typically, one of these columns is a primary key in one table and a foreign key in the other table. These are related through a join to combine the data correctly based on matching values in those key columns. In this video, you learned the purpose and types of join clauses in SQL. Joins are essential when working with relational databases. They allow you to combine data from multiple tables based on their relationships. By understanding the different types of joins, the importance of primary and foreign keys, and their syntax, you can query your data more effectively and answer complex questions. Imagine you're working with data from different departments in a company. customer information in one table and order details in another. It feels like you're trying to put together a puzzle with pieces from different boxes. How do you make sense of it all? That's where SQL joins come in. Joins allow you to connect data from separate tables, helping you to get the full picture and make informed decisions based on the combined data. In this video, we will write SQL queries using different types of joins to retrieve combined data. Before we explore some examples and write queries using join, let's review the general syntax of a join statement. Recall that the basic structure of a join starts with the select statement, where you pick the columns you want. Next comes the from clause, where you name the first table, usually called the left table, in the join. Next, the join keyword is followed by the second table name, referred to as the right table in the join. We finish with the on clause, which tells SQL how the two tables are related. You simply match the columns from each table, like table1.column equals table2.column. Typically, one of these columns is a primary key in one table, and the other is a foreign key in the related table. This relationship allows the join to combine the data correctly based on matching values in those key columns. Now that we've covered the basic join syntax, let's put it into action. We'll start by working with two tables, customers and orders. As we discuss each type of join, you'll notice how they help us combine data in different ways. The customers table includes columns for customer ID, a name, and a date of first order column. In this table, there are 4 rows. The first row is customer 001, whose name is John. The date of the first order is 05/17. The second row is customer 002, named Anissa, with a date of first order of 06/01. The third row is customer 003, named Mark, but no date for the first order is provided. And the fourth row is customer 004, named Penelope, with a date of first order of 06/24. The orders table includes columns for an order ID, a customer ID, and an order amount. In this table, there are also 4 rows. The first row is order 0102, placed by customer 001, with an order amount of 20. The second row is order 0103, placed by customer 008, with an order amount of 40. The third row is order 0104, placed by customer 002, with an order amount of 22. And the fourth row is order 0105, placed by customer 004, with an order amount of 30. Let's now use these tables in some advanced join examples. Let's say you want to find all customers who have made a purchase. To do this, you would use an inner join between the customers and orders tables. Remember that an inner join returns only the rows where there is a match in both tables. Start with the select statement, where you list customers.name and orders.orderID separated by a comma. Then use the from clause to pull data from the customers table, followed by inner join orders. Finish with the on clause, which links customers.customerID to orders.customerID. This query will return all customers who have placed an order, along with the corresponding order IDs. In the result, we have 3 customers, John, Anissa, and Penelope. John, who has a customer ID of 001, placed an order with the order ID 0102. Anissa, with customer ID 002, placed an order with order ID 0104. And Penelope, with customer ID 004, placed an order with order ID 0105. Mark, whose customer ID is 003, does not appear in the result because there is no matching entry for him in the orders table, meaning that he hasn't placed any orders. Similarly, any orders not tied to a valid customer ID, such as order ID 0103, which has a customer ID of 008, are also excluded, since no match exists in the customers table. Next, what if we want all customers, including those who haven't made any purchases yet? That's where the left join comes in to return all the rows from the left table. In this case, the customers table. The syntax for this is the same as the inner join, except you replace the join clause with left join. The syntax is select customers.customername, orders.orderID from customers, then left join orders on customers.customerID equals order.customerID. This ensures that even customers who haven't placed an order are included in the results, with any missing orders details appearing as null. In the result, we see 4 customers: John, Anissa, Penelope, and Mark. John with the order ID 0102, Anissa with the order ID 0104, Penelope with the order ID 0105. Mark appears in the result, but since he hasn't placed any orders, his order ID is listed as null. This is the key difference in a left join. Mark is included even though there is no matching order for him. However, any orders not tied to a valid customer, like order ID 0103, are still excluded because the left join prioritizes customers over orders. Now, let's reverse things. If you want to focus on all orders, including those that don't have matching customers, a right join is the way to go. Like the left join, the syntax is almost identical, just change left to right. The syntax is select customers dot customer name, comma orders dot order ID from customers, then right join orders on customers dot customer ID equals orders dot customer ID. This query will return all orders, including those with no matching customers. In the result, we have 4 orders, 3 linked to customers and 1 that isn't. John placed an order with the order ID 0102. Anissa placed an order with the order ID 0104, and Penelope placed an order with order ID 0105. We also have order ID 0103. Since there is no matching entry for customer ID 008 in the customers table, the customer name for this order appears as null. Mark, whose customer ID is 003, does not appear in the results because he hasn't placed any orders, and a right join only includes customers if they have corresponding orders. Finally, what if you want to get everything, all customers and all orders, whether or not they match? That's when you use full outer join. This join ensures you won't miss any customers or orders, even if they aren't directly related. As with the others, the syntax for this is the same as an inner join, except you replace the join clause with full outer join. The syntax is select customers dot customer name, comma orders dot order ID from customers, then full outer join orders on customers dot customer ID equals orders dot customer ID. This query will return all customers and all orders, even if they are not related, with any missing information filled as null. In the result, we have 4 customers and 4 orders. John, who has a customer ID of 001, placed an order with the order ID 0102. Anissa, with customer ID 002, placed an order with order ID 0104. And Penelope, with customer ID 004, placed an order with order ID 0105. Mark, whose customer ID is 003, is included in the result even though he hasn't placed any orders, so his order ID and order amount are null. Similarly, order ID 0103, which has a customer ID of 008, is also included, but since there are no matching customers for customer ID 008, the customer information appears as null. A full outer join ensures that both customers and orders are included in the result, even if they don't have corresponding matches in the other table. In this video, you learned how to write SQL queries using different types of joins to retrieve combined data. Whether you're working with data like customers and orders or handling information from other industries, SQL joins allow you to combine and analyze related data efficiently. Data is more than static rows and columns. It represents dynamic information that can be used for various purposes. Raw data often requires reshaping and transforming to fit analysis or reporting needs, like combining names or extracting specific portions for clarity. SQL provides powerful functions that allow us to manipulate data so that it can be better understood and applied to real-world needs, like creating reports, generating insights, or improving user experiences. In this video, we will explain the basic SQL functions used for data manipulation and transformation. Let's start with a definition of what a SQL function is. SQL functions are predefined operations in SQL that allow you to perform specific tasks on your data, like manipulating or transforming it. These functions can modify text, calculate values, extract information, or aggregate data, making it easier to retrieve and present data in a useful format. SQL functions are typically used within SQL queries to process data directly from the database's tables without the need for external programming. Now, let's explore some of the most commonly used SQL functions that make data manipulation easier, starting with concat. The concat function allows you to join multiple strings into one. For example, if you want to combine a first name and a last name into a full name, concat is the tool you'd use. The concat function is used in a select statement to combine multiple expressions, such as table columns, literal values, which are text or numbers in quotes, or calculations into a single string. Let's say we have a music catalog table with two columns, artist first name and artist last name. To combine these into one column as the full artist name, we would write the query select concat, followed by artist first name, a space in quotes, and artist last name inside parentheses, and separated by a comma. We follow that with as artist full name to create an artist's full name alias. Finally, we use from music catalog to identify where we are pulling the data from. In this example, concat combines the first and last names with a space in between, transforming two columns into a single meaningful string. Now that we've combined strings using the concat function, you might need to measure the length of a piece of text. That is where the len function or length function comes in. It helps you count the number of characters in your data. The len function is used in a select statement to calculate the number of characters in a given expression, including spaces and punctuation. To find the length of all the artist's last names, we would write the query select len. After len, we add artist last name inside the parentheses. Then we use as last name length to create an alias for the result. Finally, we use from music catalog to specify the table from which we are retrieving the data. After combining and finding the length of text, there might be times when you need to standardize it. For example, the upper function is perfect for converting names or text to uppercase for consistency. The upper function converts a specified expression to uppercase, using the syntax of the upper keyword followed by the expression in parentheses. To convert all the artist names to uppercase, we would start the query with select upper. Inside select upper, we include artist first name in parentheses. Then we use as artist first name upper to create an alias that labels the result as the uppercase version of the first name. Finally, we specify from music catalog to indicate where the data is coming from. Just as you sometimes need to convert text to uppercase, there are cases where lowercase is needed. To do this, you can use the lower function, which converts text to lowercase. The lower function, used in a select statement, converts a specific expression to lowercase, using the syntax of the lower keywords followed by the expression in parentheses. For example, to convert all the artist's email addresses to lowercase, we write the query select lower, followed by the column name artist email address inside parentheses. We then follow that with as artist email lower to create an alias representing the email address in lowercase. Next, we add from music catalog to specify that we are pulling the email address from the music catalog table. Lastly, let's explore the SQL function that enables us to extract part of a string. Whether you need the first few letters of a name or just part of a text field, the substring function allows you to select exactly the portion of text you need. It extracts a part of a string based on your specific starting point and length. The substring function is used in a select statement to extract a portion of a string. It follows the syntax of substring keyword, an expression, a starting position, and the length of the substring in parentheses. The starting position indicates where extraction begins, while the length specifies the number of characters to extract. For example, if you want to display the first 3 letters of each artist's last name for easier sorting or categorization, you can use the substring function. The query would start with select substring, then in parentheses include artist last name followed by a comma and the starting position, which in this example is 1, another comma, and then the length of the substring, which is 3. Finish the query with as artist last name snippet from music catalog. This extracts 3 characters from artist's last name starting at position 1 and then creates an alias for the shortened version. In this video, you learned some basic SQL functions used for data manipulation and transformation. The more you apply these techniques, the more intuitive they will become. Keep exploring, and you'll soon notice how powerful SQL functions can be in managing and transforming data. When working with large datasets, interpreting raw data can be overwhelming. Aggregate functions in SQL allow you to calculate sets of data into a single result, revealing patterns and trends. In this video, we will describe the use of aggregate functions to perform calculations on data. Let's start with a definition of what aggregate functions are. SQL aggregate functions are functions that perform calculations on a set of values and return a single value. This single value is used to extract meaningful metrics and provide insights through summarization. Like other functions, they're often used in select statements to summarize data. With that in mind, let's explore each aggregate function in action, starting with the count function. The count function returns the number of rows that meet a specific condition, making it useful for determining how many entries satisfy certain criteria. To use the count function, place it after the select statement, where you normally list the columns. For example, to count the total number of songs in a music catalog table with a column called song title, the query starts with select count with an asterisk in parentheses, which counts all rows. Using an asterisk counts all entries, while specifying a column name counts only non-null values. Next, add as total songs to give the result an alias and provide a meaningful name. Finally, use from music catalog to indicate the data source and finish the query with a semicolon. In our example, count with asterisk in parentheses returns the total number of songs in the table. While count determines the number of entries that meet a certain criteria, the sum function provides the total of a column's values. Instead of counting entries only, sum adds each value in the specified column to provide a total of all values. This makes it an essential function for analyzing totals across large data sets. Similar to count, the sum function is used in the select statement to aggregate data. For example, if our music catalog table has a revenue column that tracks total sales generated by each song, we can find the total revenue by starting with select sum with revenue in parentheses. We then add as total revenue to give the result an alias and complete the query with from music catalog to specify the data source. In this example, sum with revenue in parentheses calculates the total sales revenue by adding up all values in the column. Now that we have explored the sum and count functions, let's explore the AVG or average function, which helps determine the average, such as the average sale amount or revenue per item. AVG computes the average of all values in a numeric column by dividing the total by the number of entries, offering insights into overall performance. To calculate the average revenue per song, we start with the query select AVG with a revenue in parentheses. This places the column name in parentheses to specify the values to average. We then add as average revenue to provide an alias for the result and end the statement with from music catalog to specify the data source. In this example, AVG with a revenue in parentheses calculates the average revenue generated by all songs in the catalog and returns the average sales amount per song. Knowing the average is helpful, but you may also want to identify specific data points, like the lowest revenue or least popular product. We can use the min function to do this. The min function finds the smallest value in a specified column by directly retrieving the lowest value in your dataset. To find the lowest revenue generated by a song in the music catalog, we use min. The query begins with select min, placing the column name in parentheses. We then add as lowest revenue to provide an alias for the result and conclude with from music catalog to indicate the data source. In this query, min revenue returns the smallest sales revenue amount, identifying the song in the catalog with the lowest revenue. Just like how min helps you find the smallest value, the max function identifies the largest value in a column. To find the highest weekly plays for a song in the music catalog, we use max. The query begins with select max weekly plays, placing the column name in parentheses. We then add as highest plays to create an alias for the result and conclude with from music catalog to specify the data source. In this example, max weekly plays returns the highest number of weekly plays recorded for any song in the catalog. We've now explored the aggregate functions, count, sum, average, min, and max, and you understand how each one allows you to get different insights from your data. However, these functions become more powerful when combined with the group by clause. The group by clause groups rows with the same values in specified columns into summary rows, and is commonly used with aggregate function. For example, to find the total revenue generated for each music genre in our catalog, we would use sum with group by. The query starts with select genre, followed by sum revenue as total revenue, and concludes with from music catalog group by genre. This setup calculates the total revenue for each genre by grouping the data accordingly. In this video, you learned how to use aggregate functions to perform calculations on data. Keep experimenting, and you'll soon notice how powerful aggregate functions can be for any analysis task.
In this lab, we're going to be using a database called EmployeeDB to practice applying SQL functions and using aggregate functions so we can manipulate data and analyze it using SQL queries. So the first thing we want to do, I'm in the MySQL prompt here. The first thing we're going to do is create that database. So I'm going to create the employees and DB, which will be our sample DB. And then I'm going to make sure I'm using that database. All right, so now we're in the database and we can start to manipulate it and populate the database with some data. The first thing we're going to do is create an employees table. So this is now step 2. So in step 2, we're going to set up our employees table and then populate it with some data. So in this query, we're going to use the create table command. We have fields here: employee ID, first name, last name, department, salary, and hire date. Each has its own data type. You'll notice that employee ID is set to auto increment, and it's also the primary key. So we don't have to pass in data to that field. That will be created automatically and just increment the number from the previous one that was created. And the other data we will have to pass in and populate. So let's do that next. We're going to insert now into employees a set of sample data that we can use to run further queries. So we now have 7 records created: the first and last name, the department they're in, how much their salary is, and when their hire date is. Notice we didn't have to pass in the ID because that's created by SQL. Now we're going to query the data now that we have it in there using some select statements. And we can use various functions with our select statements. So the first one we're going to do is concatenate the first and last name to get a full name back from the query. So we're going to use this concat, put a space between the first and last name, and we'll get it back as a full name. So now we get every user in the database, every person in the database, employee, and we have their first and last name separated by a space. You'll remember that when we put the data into the database for the departments were not capitalized. They were sentence cased. So this function, the upper, will make the department names uppercase, and we're going to get back a table from the employees database with all the department names uppercased. That's just a simple little function that allows us to capitalize all the names. And then finally, we're going to use this command, which will just give us the length of the first name. It's probably not a very practical query on the surface, but there are situations where you do need to figure out the length of something. If a database that you're transferring data to can only accept a certain amount of length for a specific field, you may want to test that length and figure out where you need to concatenate or reduce the size in order to make the data fit in the target database. Now in step 3, we're going to use aggregate functions. These functions will allow us to do things like count, get the average of something, the max. So we'll use these queries to demonstrate how you can use further features of SQL query language to really dig into your data and get the exact data that you need. So this one is just counting the employees, all the employees in the database, and we're saying count everything and then return total employees as a table from the data in the employees table. That can be very useful in a lot of scenarios. This is a very simple data set, but you can imagine how doing something like that can be useful for doing aggregate functions. Now we're going to get the average salary for all the employees. It comes out to 74,000. And again, that's just a nice function to use when you're working with large numbers. The max salary, this will look at the maximum salary across all the employees in the database and pick out the one that's the highest. And then this one is the lowest salary. So highest earner is 93,000 in this database and 60,000 for the lowest earner. And this min and max prevent you from having to go over every row manually. It just provides that single data point by using that method, that function. Now in step 4, we're going to use the group by feature or function in SQL query language. We're going to select the salaries, but we're going to group them by department as our first query. So here we select the department, we sum the salaries as the total salary, which you can see that column on the right, from the employees table, and we're going to use the group by department. So now we know engineering has a sum salary of 178,000, marketing 149,000, etc. So this allows us to group them by the department using that group by function. And now let's do the same, but this time we're going to count how many employees are in each department. Still grouping by department, and we're just getting an employee count instead of the salary. For our final step, we're going to use the concatenation function along with the average and the where clause. So here we're combining a number of different functions to provide a single return value. And you can get your SQL statements can get very, very complicated, but they're also very powerful. So here we're going to concatenate the first and last name as the full name. That gives us our first column. We average the salary. That gives us the average salary for the second column. And then we're also looking at where the hire date is greater than January 1st, 2020. And that gives us one name back. And this person has an average salary of $69,000 a year. We can grab that because we can use these multiple functions in a single select statement. Instead of having to write multiple statements to do this work, we can write it as a single statement, and it's consolidated and it can be very powerful. So using SQL statements, you can do a lot of work against data. This is a very simple database schema with very simple data, but you can imagine using SQL query language in this context to produce some very powerful queries to manipulate and analyze your data.
As you've discovered, mastering SQL's core syntax and functions is key to effectively managing and querying data. From retrieving information to performing advanced calculations, your understanding of SQL enables you to handle data efficiently and gain valuable insights. We began this module by outlining the fundamental syntax of SQL and explored how this essential language functioned within databases. Next, you learned how to retrieve data with select statements, focusing on querying databases efficiently to extract the information you require. Then, you explored how to manipulate data using insert, update, and delete statements, developing the skills to modify and manage data effectively in SQL. After that, you focused on merging data from multiple tables using SQL join clauses, gaining the ability to construct complex queries that seamlessly integrated data. Lastly, you explored SQL aggregate functions, mastering advanced calculations and data transformations to uncover valuable insights. Mastering SQL is essential for effectively managing and querying data. By honing these skills, you'll be able to handle complex data operations, enhancing data accuracy, and drive deeper insights, ultimately boosting the effectiveness of your database management. Welcome to Advanced Data Handling. In today's data-driven world, efficient and secure database management is crucial for building reliable backend systems. This module covers essential skills for optimizing SQL queries, managing transactions, and securing databases. You will begin by examining advanced SQL query techniques, focusing on methods to enhance query efficiency and manipulate complex data structures effectively. Next, you will explore performance tuning and optimization techniques for SQL queries, which will help you identify issues, optimize query execution, and boost database performance. Then, you will acquire skills in transactions and concurrency controls in SQL, learning how to manage multiple user environments, ensure data integrity, and address common concurrency challenges. After that, you will explore using stored procedures and functions in SQL, learning how to streamline database operations and improve code reusability. Finally, you will identify security best practices for SQL databases and examine techniques to protect data, prevent SQL injection attacks, and safeguard sensitive information. By the end of this module, you'll have the skills to optimize SQL queries, manage transactions, and confidently secure your databases. Let's start with advanced data handling and address the complexities of backend development together. The use of subqueries and common table expressions, or CTEs, in SQL can open new ways to manage complex data, giving you the power to seamlessly combine and filter results across multiple sources with precision. By combining SQL commands you've already learned with a few new query building strategies, these techniques can transform basic SQL into powerful tools for taking on complex data challenges. In this video, we will explain the use of subqueries and CTEs in SQL queries. Both subqueries and common table expressions, or CTEs, are advanced querying techniques that make complex data retrieval more manageable. They allow you to nest and organize SQL commands for powerful layered results. Let's begin by first defining what subqueries are and then describing how they're used. A subquery is a query nested within another query. Subqueries are often used to filter data, calculate values, or join tables based on specific criteria. So how do subqueries work? In SQL, a subquery, also called an inner query, runs first and returns results that an outer query uses to further process or filter the data. Subqueries can be used in different parts of a SQL statement, like the select, from, or where clauses. They can also be used in commands like insert, update, or delete, anytime you need results from one query to feed into another. Subqueries are also commonly used to compare an expression to another query's results, such as checking if a value is equal, greater than, or less than something found by a subquery. They're also useful for checking if a value appears in a list of results. When working with lists, operators like in allow you to check if a value exists in the list, while any and all are useful for specific comparisons. Let's use the example of a music catalog. Suppose you want to find all songs by artists who have more than 1 million followers. First, you'd create a subquery to identify artists who meet this follower threshold. You would write this query as select artist ID from the artist table where followers is greater than 1 million. Then, you'd use this subquery within the main query to retrieve songs from those artists. The full query would begin with select song title from the songs table, then you add the condition where artist ID is in, and next in parentheses you add the subquery select artist ID from the artist table where followers is greater than 1 million. Then finish the query with a semicolon. Let's examine what the inner and outer queries are doing here. The inner query, or subquery, executes first, returning a list of artist IDs for those who meet the follower threshold of greater than 1 million. The outer query then selects song titles from the songs table, but only for artists whose artist ID matches those from the subquery. This layered structure simplifies finding relevant data across related tables. Now that we've explored how subqueries can layer logic within SQL, let's explore another advanced querying technique, Common Table Expressions, or CTEs. Let's start with a definition. A common table expression, often abbreviated CTE, is a temporary result set that can be referenced multiple times within a single SQL statement. CTEs can be thought of as temporary tables that exist only for the duration of the query. CTEs let you break down complex queries into smaller parts, making them easier to manage. CTEs are particularly helpful when you need to reference the same result more than once, as they improve readability and clarify your query structure. CTEs are defined using the with clause, followed by a CTE name and the keyword as. To build on our previous example, let's suppose you want to calculate the average popularity score for songs by artists with more than 1 million followers. Then you want to use this score to exclude songs that fall below this popularity threshold from the results. Let's start to create a CTE with the name popular artist, using the syntax with popular artists as. Then, inside the parentheses, we define the query that will generate the CTE by selecting artists and using AVG for average to calculate the average popularity score for each artist from the songs table. We name this average as AVG popularity. Finally, we add a where clause to specify that we only want to include artist ID with more than 1 million followers. To do this, we use a subquery. This inner query, denoted using the keyword in, selects artists from the artist table where the number of followers exceeds 1 million. Only artists who meet this condition will be included in our popular artist CTE, allowing us to focus on those with significant follower counts. Now, we can use the popular artist CTE in the main query to join its results with the songs table and exclude any songs that fall below their artist average popularity threshold. You can start by selecting the song ID with select s.songid from the songs table. You add an alias for the song table as s for simplicity by placing the alias immediately after the table name in the from clause. Then use join with popular artists, which is our CTE. Use the artist ID as the matching key between the tables. This join brings in only the artists with enough followers and their average popularity scores. In the where clause, select songs with a popularity value that meets or exceeds their artist's average popularity. Now that you've been introduced to the use of subqueries and CTEs, let's explore when they should be used. The main difference between subqueries and CTEs is in their ability to handle complexity. Subqueries work well for simpler or single-use queries, while CTEs excel when you need to reuse a query, break down a complex query into smaller parts, or improve readability. In this video, you learned about the use of subqueries and CTEs in SQL queries. Mastering these advanced querying techniques can elevate your SQL skills and enhance your ability to write efficient, maintainable SQL queries. In SQL, filtering data is one of the most important skills for getting useful information from a database. While simple queries are enough for basic tasks, real-world problems often need more advanced filtering methods. This is where learning about more advanced SQL techniques may be needed. In this video, we'll describe advanced filtering techniques and complex SQL queries. Advanced filtering techniques in SQL give you the power to refine your queries and retrieve data based on more complex conditions. These techniques include the use of comparison operators, logical operators, pattern matching, conditional logic in where clauses, and aggregate filtering in the having clause. Let's start with comparison operators, which are used in nearly every query. Think of comparison operators as the core tool in SQL filtering. They let you compare values like numbers, dates, or text so you can find exactly what you're looking for. Imagine you need a list of employees with an exact salary of $50,000. In this case, you'd use the equals operator just like you would in any basic math problem, adding salary equals 50,000 in the where clause. Let's say you need to find employees who earn more than $100,000. That's where the greater than operator comes in. You'd simply write salary with a greater than symbol followed by 100,000 in the where clause. And if you needed to find employees with salaries less than $100,000, you'd write salary with the less than symbol and $100,000. If you want to query for results that are less than or greater than a value, including the value itself, you can add an equal to. For example, to find salaries less than or equal to $50,000, you would use salaries with both the less than and equal to symbol followed by 50,000. And then there's the does not equal operator to filter out employees whose salary is not $50,000. These comparisons are the foundation of filtering data. So far, we've explored how comparison operators can help you filter data based on a single condition, but often you need to refine your queries further by adding more criteria. This is where logical operators come in. Logical operators allow you to combine or exclude conditions. For example, if you want to find employees with more than 5 years of experience who work in IT, you can use the AND operator. By using the AND operator, both conditions need to be true: employees with more than 5 years experience and those who work in IT. If you're interested in employees either in IT or with more than 5 years of experience, then you'd use the OR operator. The OR operator means only one of the conditions has to be true: either employees with more than 5 years experience or employees who work in IT. So far, we've focused on filtering based on numbers and exact conditions. Now, let's explore how we can filter based on patterns in text or a set of specific values using pattern matching. Pattern matching allows you to search for partial matches or values within a set. The like operator uses a wildcard, the percent symbol, to help you find data that follows a pattern. For example, if you want to find employees with names starting with John, you will add the keyword like, a space, then John, followed immediately by a percent sign to your query. The text of John percent sign needs to be in single quotes. You can also use in to match against a list of values, like retrieving employees in the IT, finance, or marketing departments. You would do this by using the keyword in and in parentheses list the values to match against. For this example, you will include the keyword in and open parentheses and the list IT, finance, marketing, and close the parentheses. Now that you know how to filter based on patterns and lists, let's introduce conditional logic. Conditional logic allows you to search for different values based on specific conditions. The case statement adds some programming logic into SQL. It's similar to using an if-then statement in code to check for certain conditions and return a value based on the result. Imagine you want to label employees based on experience. You could use case to classify them as junior for less than 2 years, mid-level for 2 to 5 years, and senior for more than 5 years of experience. This lets you customize the output of your query based on specific criteria, adding more flexibility to how you present your data. So far, we've been filtering individual rows, but what if you want to filter groups of rows, like finding departments that have more than a certain number of employees? That's where aggregate filtering comes in. Aggregate functions summarize data across multiple rows. For example, you can add up or count the number of employees working in the company using the count function and employee ID in parentheses immediately after it. This will count each employee ID and return as a result the number of employees in the company. You can use the function AVG to find the average. To find the average salary, you will type AVG followed by salary in parentheses. This will go through all of the salaries in the salary column and calculate the average salary. If you wanted to find the lowest or min salary, you can use the min function, MIN followed by salary in parentheses. And to find the highest or max salary, you can use the max function, MAX followed by salary in parentheses. If you want to find the total of all salaries, you can use the add function, ADD followed by salary in parentheses. After applying an aggregate function, there might be times when you want to filter the summarized results, and that's where the having clause comes in. The having clause is similar to the where clause, but it's used to filter aggregated results. Say you've used count to find the number of employees in each department, but you only want to display departments that have more than 50 employees. For this example, you'd use having count with employee ID in parentheses greater than 50 to filter the results after aggregation. While where filters rows before aggregation, having filters rows after the aggregation has been applied, which is key when you're working with grouped data. In addition to advanced filtering techniques, you might encounter complex situations where you need to join data across multiple tables in more complex ways. Advanced joins are useful when your queries require combining data from multiple sources or performing more intricate filtering. Often, you'll need to join 3 or more tables to get all the data you need. For example, if you're working with an employee database and want details about employees, their departments, and the projects they've been assigned to, you'll perform joins across the employees, departments, and project tables. As you add more tables to the join, your query becomes more complex, but allows you to gather more comprehensive information across your data set. In other situations, instead of joining many tables, you may need to filter data in one table based on conditions from another table. In these cases, using subqueries within joins allows you to filter data first and then join the results with another table. For example, if you're looking for employees working on projects with budgets over a certain threshold, you can use a subquery to filter projects based on their budget from the project table. Then you join that filtered project data with the employee table. This approach gives you more control, as the subquery filters the data before the join happens, making the query more precise. For even more complex queries, when you need to manage intermediate calculations or results before performing a join, use common table expressions, or CTEs. They're an effective way to handle the logic in steps. For example, you could use a CTE to calculate the average salary for each department and then join that result with another table to compare individual employees' salaries with their department's average. CTEs allow you to structure your query step by step, making complex joins easier to manage. In this video, you learned about advanced filtering techniques in complex SQL queries. As you practice these skills, you'll find that the ability to create complex queries will become a valuable tool for pulling the exact data you need, giving you more precision and confidence in your analysis. Efficient SQL queries aren't just about speed. They're about making sure data retrieval is as smooth and resource-friendly as possible. Small adjustments can make a big difference, transforming a slow database into a responsive one. We call this performance tuning. In this video, we will describe the importance and basics of SQL query performance tuning. To start, let's cover what can slow down SQL queries and why tuning them is essential. Inefficient queries can delay results by retrieving too much data or not filtering properly. This is where the SQL optimizer comes in. The SQL optimizer is the brain of SQL queries. It finds the fastest, most efficient way to execute each query. Like a GPS choosing the best route, the optimizer creates an execution plan, which outlines the steps for retrieving data based on available indexes, joins, and sorting options. An execution plan acts as a map for data retrieval. By reviewing it, developers can spot inefficiencies, like a full table scan instead of using an index. If a query is slow, analyzing the plan can reveal where improvements, like adding an index, will boost performance. With this foundation, let's look at some easy techniques to reduce data processing and speed up queries. When writing a select statement, it's best to specify only the columns you need, rather than using select with an asterisk. This reduces the amount of data the database has to pull and process, which can save time and resources. If you only need to see a product's name and price, using select product name, price from products pulls just those 2 columns, while select asterisk from products retrieves all columns, adding unnecessary load to the database. By reducing the data retrieved, this approach saves resources and makes the query faster. Another technique is to use a where clause. This lets you narrow down results by specifying criteria, so the database returns only the data you need. This saves resources and speeds up your query because it doesn't have to retrieve irrelevant rows of data. Suppose you only need products priced under $20. Adding where price is less than 20 filters out all other products, so the database only retrieves rows that match. This avoids wasted processing time on rows that aren't relevant, speeding up the query. Sometimes, when a query retrieves data from multiple related tables, duplicates can appear in the results. The distinct keyword removes these duplicates, keeping the results clear and saving processing time by reducing the data the database has to handle. Imagine you want a list of unique product categories from a large product database. Using select distinct category from products returns only unique categories, reducing the number of rows in the results and making the query faster. If you're working with a large dataset but only need a preview, the limit keyword reduces the number of rows the database has to return. For example, if you only need to see the first 10 products, select asterisk from products limit 10 retrieves just those rows, making the query quicker. This is especially helpful when dealing with large tables, where retrieving every row would slow things down. In this video, you learned about the importance and basics of SQL query performance tuning. Small improvements to SQL queries don't just save time, they transform how databases respond to users. By applying basic performance tuning techniques, you're building a foundation for efficient data management that you can scale with any application. Optimizing SQL queries is like tuning an engine. When done right, it can dramatically boost performance, especially in high-traffic systems. In this video, we'll describe techniques for optimizing SQL queries to enhance performance. Let's begin by exploring the SQL optimization technique of indexing. Recall that indexing is a technique that creates a data structure on one or more columns of a table, enabling a database to quickly locate specific rows without scanning the entire table. For example, if you index a column with unique employee IDs, the database can retrieve data in a structured way, minimizing the number of rows it needs to scan. There are several types of indexes, but let's focus on two common ones. A single column index works on one column only, like an ID or date column, which is great when you need to search by a single value. A composite index includes multiple columns, helping optimize queries that filter on multiple fields. For example, if a query searches by both department and location, a composite index on these two columns would enhance performance more than individual indexes on each. Beyond indexing, understanding how the database organizes and plans to execute the entire query is essential for optimizing performance. This is where query planning comes in. Recall that the SQL Optimizer creates an execution plan, which is a sequence of steps that the database follows to execute a query. By reviewing the execution plan, we can evaluate whether the database is choosing an efficient path or if there's room for improvement. Execution plans vary by database, but one common element includes scan efficiency. Scan efficiency is the effectiveness with which a database scans a table to retrieve data, typically done as either a full table scan or as an index scan. When there's no index, the database relies on a full table scan, checking each row in the table, which is slower, especially with large datasets. Adding or modifying indexes results in an index scan, which can improve scan efficiency. With an index scan, the database can go directly to the relevant data. Along with scan efficiency, execution plans improve the efficiency of any joins being performed. Join efficiency is the effectiveness with which a database combines data from multiple tables. Join operations are displayed in the execution plan, and high-cost joins may signal an opportunity to improve join efficiency. Restructuring or reordering joins, like processing smaller tables first, reduces the amount of data the database handles simultaneously, enhancing overall query performance. While indexing and query planning are powerful optimization techniques, there are other practical strategies to optimize queries. Let's explore a few of the most effective ones. Sometimes, rewriting a query slightly can make a big difference. For example, using join instead of a subquery may reduce execution time. Alternatively, Using the keyword exists instead of in when checking for values in a related table can speed things up. Along with rewriting queries, avoiding unnecessary computation or conditions can also improve performance. For example, instead of using select asterisk, list only the columns you need to reduce the amount of data processed. Also, be sure to include where statements in your query to filter results. This minimizes the database's workload and speeds up retrieval. Finally, it is crucial to retrieve only what is necessary for large data sets. This is done by limiting data retrieval using pagination. Pagination is the process of dividing a large result set into smaller, manageable pages to limit data retrieval and improve query performance. For instance, using the keyword limit and offset in a SQL query allows you to retrieve a smaller number of records at a time. This is especially useful when displaying data in applications where working with 100 results per page is more efficient than fetching thousands at once. In this video, you learned about techniques for optimizing SQL queries to enhance performance. Optimizing SQL queries helps us keep our databases responsive and our applications running smoothly. By using indexing, understanding query plans, and employing smart optimization strategies like query rewriting and pagination, we can make significant improvements to query performance. With these techniques, you're well equipped to take on larger datasets efficiently. Whenever we make database changes, we rely on them to happen smoothly and accurately. SQL transactions build trust by ensuring data remains consistent no matter what. In this video, we will explain the concept of transactions in SQL and their role in maintaining data integrity. First, let's define what a SQL transaction is. In databases, a SQL transaction is a sequence of operations performed in a single logical unit of work. Think of it as a package of changes where each part depends on the others to succeed. If one part fails, the whole transaction is rolled back, preserving data accuracy. With that understanding, let's explore the ACID properties, 4 principles that guarantee transaction reliability. ACID is an acronym that stands for atomicity, consistency, isolation, and durability. Let's now explain each of these, starting with atomicity. Atomicity is the principle that a transaction is one complete, unbreakable action. Either everything within the transaction happens or nothing happens. If even one part of a transaction fails, none of the changes are applied. This property prevents partial updates, which could lead to errors. Think of transferring funds between 2 accounts in a banking system. 2 steps must occur: subtracting an amount from one account and adding it to another. Moving forward, let's discuss the next property, consistency. Consistency is the principle that ensures a transaction moves the database from one valid state to another, following all rules, constraints, and data integrity requirements. This principle stops any changes that would make the database incorrect or break its rules. It keeps things accurate by ensuring every update follows all data requirements. For example, if a bank is processing a transfer, it won't allow the bank balance to drop below 0, ensuring account records remain valid. Next, let's focus on isolation, another key property for managing multiple transactions simultaneously. Isolation is the principle that ensures each transaction operates independently, so changes from one transaction don't affect others until they are all complete. When multiple transactions occur at the same time, isolation prevents them from interfering with each other's data. So even if transactions overlap in time, each one operates as if it's the only transaction in progress, avoiding issues like data mismatches or accidental overwrites. For example, if 2 users try to update the same account balance at the same time, isolation ensures that each update happens independently. Finally, let's address the last property, durability. Durability is the principle that ensures complete changes are saved permanently, even if the system crashes. Durability ensures that the results of a committed transaction persist, providing reliability for data storage. For example, after a bank transfer is complete, durability ensures the updated balances are saved permanently, so they remain accurate even if the system goes down right after. Now that we've reviewed the ACID properties, let's discuss the specific SQL commands used to control transactions. To work with transactions in SQL, we use specific commands like begin, transaction, commit, and rollback to control them. Let's start with the begin transaction command, which marks the start of any transaction. Begin transactions is the command that starts a transaction, grouping the following actions as a single unit. Once we use this command, any operations performed after it become part of a single transaction until we either commit or roll back the changes. Recall the situation where you need to transfer funds between two accounts. Here's how you would use the transaction command for this transfer. First, start with the begin transaction to signal that everything happening next is part of this transaction. Then, you subtract the funds from the sender's account and add them to the recipient's account. With the transaction started, let's continue to the next command, commit. Commit is the command that finalizes a transaction, saving all changes permanently to the database. It signals that the transaction has been successfully completed and that the ACID properties have been upheld, ensuring data integrity. In the bank transfer example, if both actions, subtracting from the sender and adding to the recipient, succeed, commit would save these changes permanently, confirming that the transaction is complete and accurate. If something goes wrong during a transaction, we have the rollback command to reverse the changes. Rollback is the command that cancels a transaction, undoing all changes made since the transaction began. If an error occurs or if any part of the transaction fails, we use rollback to maintain data accuracy by discarding the incomplete changes. Continuing with our transfer funds example, if anything fails along the way, maybe the sender has insufficient funds, then rollback would reverse everything, leaving both accounts as they were before the transaction began. This process keeps the accounts balanced, ensuring data integrity, which is exactly what ACID properties protect. Using begin transaction, commit, and rollback together allows us to manage complex operations confidently, knowing that the database remains reliable, consistent, and accurate. Transactions like this are essential for applications where data consistency is crucial. In this video, you learned about transactions in SQL and their role in maintaining data integrity. Transactions make sure that data stays intact and dependable, even through complex changes. By understanding and using transactions, you're not only managing data, but also creating a foundation for reliability that supports every interaction within a database. Transactions are always running in a database, often at the same time, and each one might need access to the same data. When multiple transactions overlap, they can clash, causing conflicts and inconsistencies. So how does a database keep everything accurate and reliable with all this activity going on? Well, that's where concurrency control comes in, managing these simultaneous transactions to prevent conflicts and keep data consistent. In this video, we will describe concurrency control mechanisms and their importance in multi-user environments. Let's begin by exploring what concurrency control is. Concurrency control is the process of managing simultaneous data access in a database to prevent conflict and ensure data accuracy. Concurrency control mechanisms are essential in SQL databases to manage transactions, ensuring that data remains accurate and conflicts are minimized. Let's now describe some common issues that can arise when multiple users work on the same data concurrently. Concurrency issues happen when one user's actions or a transaction disrupts another. The most common issues include dirty reads, non-repeatable reads, and phantom reads. Each of these issues can affect data accuracy and reliability. Let's go through them one by one, starting with dirty reads. Dirty reads happen when one transaction reads data that's been modified by another transaction but not yet committed. If the other transaction rolls back, the read data becomes invalid, leading to potential errors. For example, imagine user A changes an order status from pending to shipped, and user B views this update before it's been committed. If user A's transaction is later rolled back, The order status reverts to pending, but user B has already been informed that shipped is the status. This creates confusion and can result in decisions based on incorrect data. Non-repeatable reads occur when a transaction reads the same data multiple times and returns different results, because another transaction modified the data in between reads. For example, if user A reads a product price and then reads it again after user B has updated it, the price will be different in the two reads, creating inconsistency within user A's transaction. This could affect scenarios like tracking prices over time or auditing changes, where consistency is important. Lastly, another concurrency issue is phantom reads. Phantom reads happen when a transaction reads a set of rows matching a condition, but later notices extra rows added by another transaction that also matches that condition. Suppose user A reviews a list of orders placed today. If user B adds new orders to it shortly after, user A's next read will include more records, changing the data view within the same transaction. This can disrupt reports that need to reflect a stable data snapshot over time. Now that we've discussed common concurrency issues, let's explore how SQL handles these issues with different isolation levels. Isolation levels control how transactions interact with each other, providing various levels of protection against concurrency issues. Let's explore how isolation levels help manage these issues by controlling how transactions interact with each other. Each level offers a different balance between data protection and performance. We'll start with read uncommitted, the least restrictive level, and work our way up to the most protective level. The read uncommitted level allows transactions to read uncommitted data, which can lead to all three concurrency issues: dirty reads, non-repeatable reads, and phantom reads. It offers minimal data protection but maximum speed, so it's often used in situations where data accuracy isn't critical. For example, it can be suitable for generating quick product inventory reports or approximate order summaries. Moving up from read uncommitted, the read committed level offers more control by allowing transactions to only read committed data. This prevents dirty reads. This level balances data accuracy and performance, making it a suitable choice for many applications. Imagine an e-commerce platform where users can review product details. Read committed ensures they get committed prices, even if slight updates happen in the background. Taking it further, repeatable read offers more protection by allowing transactions to read committed data and ensures that data read once within a transaction cannot change if read again. This prevents dirty and non-repeatable reads. This level is useful when data stability within a transaction is essential. For instance, when generating invoices that must match a consistent set of product prices, repeatable reads helps keep data steady across transactions. Finally, serializable is the strictest level, treating each transaction as if it's happening alone to ensure complete isolation. This level prevents all three concurrency issues: dirty reads, non-repeatable reads, and phantom reads. Although it provides the highest level of accuracy, serializable can slow down the database due to its restrictive nature. This isolation level would be ideal for critical financial calculations, like end-of-day balances, where accuracy is paramount, even at the cost of slower processing. To support these isolation levels, database management systems implement locking mechanisms to prevent data conflicts. Locks restrict access to data, allowing only certain types of operations to proceed simultaneously and reducing the chance of concurrency issues. There are three main types of locking mechanisms: shared locks, exclusive locks, and update locks. Each lock type manages access differently to help keep transactions isolated and prevent conflicts. Let's begin with shared locks. Shared locks allow multiple transactions to read the same data, but prevent any of them from modifying it until the lock is released. This type of lock is used to reduce the risk of dirty reads. For example, shared locks are helpful when generating a daily sales report that calculates total sales from order data. By using shared locks, multiple reports can access the same data without the risk of modifying it, ensuring consistency for each report generated. Next, we have exclusive locks. that prevents other transactions from reading or modifying the data until the lock is released, ensuring that only one transaction can make changes at a time. This helps prevent non-repeatable reads and is often used in updates where data integrity is crucial. Imagine an inventory system where a manager updates stock levels. An exclusive lock ensures that while the manager updates stock quantities, no other transactions can access or change that data, preventing inconsistencies in stock levels. Finally, update locks are a hybrid approach that allows multiple transactions to indicate they intend to modify the data, but blocks each other from actually making the changes simultaneously. This lock type is useful when multiple transactions need to perform updates in sequence without causing conflict. For example, in a system where multiple sales agents update orders and invoices, update locks ensure that only one agent can adjust the same record at a time. In this video, you learned about concurrency control mechanisms and their importance in multi-user environments. Understanding concurrency issues, isolation levels, and locking mechanisms will better equip you to manage multi-user database environments. Concurrency control ensures that data remains reliable and accurate even when accessed by many users, supporting data integrity across complex shared systems. When working with databases, you'll often find yourself rewriting the same queries and managing complex calculations across different applications. This repetitive work can add significant time and effort to database management. So how can developers automate recurring queries and complex calculations while ensuring consistency and reducing errors? SQL stored procedures and functions offer an efficient solution. In this video, we will describe what stored procedures and functions are and their roles in SQL databases. Let's start with a definition of what stored procedures are. Stored procedures are sets of SQL commands saved in a database that can be run as a single task. They let us reuse code for common tasks. Instead of writing the same commands every time, we can simply call the stored procedure, ensuring consistent results while saving time and reducing errors. Some common stored procedures include user-defined procedures and temporary procedures. User-defined stored procedures are custom procedures created by developers to handle specific tasks, like updating order statuses or processing sales reports. These procedures provide flexibility and consistency for routine operations, allowing developers to create reusable code that performs complex tasks accurately and efficiently each time it's called. In addition to user-defined procedures, there are also temporary stored procedures, which are short-term procedures created for use within a single session and automatically deleted when the session ends. Temporary stored procedures are particularly useful for working with temporary calculations or data processing that don't need to be retained long-term. They help keep the database organized and efficient. Now let's discuss functions, which are a stored set of SQL statements that performs a specific calculation or operation and returns a result. Functions can be reused in queries to simplify complex calculations or data retrieval tasks. They come in two main types: scalar functions and table-valued functions. Scalar functions are functions that return a single value, like a number or a string, and are typically used for calculations or transformations on individual data elements. For example, a scalar function can calculate tax on a product price and return just the tax amount, ensuring the calculation is accurate and consistent every time it's used. While scalar functions return single values, table-valued functions return an entire table of data rather than a single value, allowing users to perform complex queries. By treating the function's output as if it were a table, it enables flexible and reusable data retrieval. For example, a table-valued function could list the top-selling products over a period, giving you data that can be queried like a regular table. This saves time by reducing the need to write complex queries each time. Together, stored procedures and functions provide multiple benefits for developers and databases. Let's explore some of these benefits. One is that they improve code organization by grouping related SQL logic, making it easier to manage and update. For example, Rather than repeatedly filtering steps in multiple queries, you can centralize them in one stored procedure, simplifying maintenance. In addition to code organization, stored procedures can significantly improve query performance. By pre-compiling and optimizing SQL commands on the database server, stored procedures reduce the need to parse and execute queries from scratch each time, speeding up database operations. For example, a stored procedure that quickly retrieves customer order histories can boost response times in a high-traffic application. Another benefit is reduced network traffic. Since stored procedures and functions run directly on the database server, there's less SQL code sent over the network, making applications more efficient. For example, instead of sending multiple queries to perform a series of calculations, a stored procedure can execute them in one go on the server, reducing back and forth communication. Lastly, they enhance security by allowing you to grant access to specific procedures or functions without exposing the entire database, protecting sensitive data. For example, you might allow users to run a stored procedure for viewing report summaries without giving them access to the underlying data tables, preserving security while enabling functionality. In this video, you learned what stored procedures and functions are and their role in databases. Stored procedures and functions are essential tools for building organized, efficient, and secure databases. By using these features, we can simplify database tasks, improve performance, and keep data safe in multi-user environments. Let's explore the practical side of stored procedures and functions, creating them. Since we're already familiar with stored procedures and functions, let's focus on writing and executing them for best practices, for ensuring the code is maintainable and effective. In this video, we will explain the process of creating and executing stored procedures and functions in SQL. We're going to start by describing the steps to creating a stored procedure. We begin with the create procedure statement, followed by the procedure name. For example, say you're creating a stored procedure for adding a new employee. Use the phrase create procedure, followed by a unique name like add new employee. After the procedure name, define any parameters that the procedure should take. List each parameter with a name and a data type. For add new employee, you'll need certain details like the employee's ID to identify who's being added and a phone number and email. In SQL, you define these parameters after naming the procedure to specify what inputs it requires. Next, add the main SQL logic that the procedure will execute. This could be any SQL command, like a select, insert, or update. Add new employee's main action is to insert the new employee's details using the insert keyword, adding their information to the database. Then, declare an output parameter using output after the data type to return a value. Inside the procedure, assign a value to the output parameter. For example, after inserting the new employee's details, you could declare an output parameter to return the new employee's ID. This output parameter ensures that once the procedure runs, it provides feedback, like displaying the unique ID assigned to the employee. Complete the procedure by adding an end statement to signal that the procedure definition is complete. Once the task is fully outlined, you close it with a completed status using end to signal that no more changes are needed. Once the procedure is created, execute it using the exec statement, followed by the procedure name and any required parameters. If the procedure has output parameters, define a variable to store the output and pass it to the exec statement. After execution, we can check the variable for the result. This approach makes procedures reusable and saves time for repetitive tasks. Now let's move on to functions. SQL functions are more specific than stored procedures, focusing on returning data that can be used within a query. We'll outline the steps to create a function as they're similar, whether it's scalar or table valued. Start with create function, followed by the function name. Imagine you're setting up a reusable formula for calculating sales tax. The function might be named something descriptive like calculate sales tax to indicate its purpose. Then define any input parameters for the function by listing each parameter with a name and data type. In calculate sales tax, the function could take the sale amount as an input, allowing it to calculate the tax based on this value. Next, you'll have to specify the return type using returns. Since calculate sales tax returns a single value, the sales tax amount, we would declare it as returns decimal. For table-valued functions, specify returns table, then add the function's logic. For scalar functions, use the return statement to specify the calculations or values you want the function to return, like a simple mathematical operation. Calculate sales tax should multiply the sale amount by the tax rate to get the tax amount. This simple mathematical operation would form the core of the function's logic. For table-valued functions, the return statement must contain a select query that retrieves a set of rows based on the input parameters. This allows the function to return an entire table of data and not just a single value. End the function with an end statement to complete its definition. Lastly, execute the function. Once defined, scalar functions can be used within a query to retrieve a calculated value, like in a select statement. For instance, if you need a calculated tax amount in a report, you can use this function in the select statement to return that calculation as part of a query result. For table-valued functions, you can use them in the from clause, treating the function like a table, which is especially useful for reusable parameterized queries. Let's now discuss some best practices to ensure the reliability and maintainability of your stored procedures and functions. First, always validate your parameters. In SQL, this means checking that each input meets specific criteria. Check inputs for valid ranges of values where necessary to prevent unexpected behavior. For example, if a parameter should always be positive, ensure it meets this requirement before processing it. Along with validating parameters, it's crucial to include error handling in your stored procedures and functions to manage issues. This way, if anything goes wrong, it catches the issue so it can be resolved without disrupting the system. You can use try-catch blocks to catch errors, log them, or return a custom message, making debugging and maintenance easier. Finally, treat stored procedures and functions like any other code, and use version control to track changes and avoid overwriting previous work. This is especially valuable in team environments where multiple people might be working on different database parts. In collaborative settings, version control ensures that each team member has insights into what others are doing and that any conflicts can quickly be resolved. This prevents issues when several people are working on related code at once. In this video, you learned the process of creating and executing stored procedures and functions in SQL. With these practices and the process of creating and executing stored procedures and functions, you now have the tools to manage your SQL logic effectively.
In this lab, we're going to be using the SQL query language to create transactions and stored procedures, and we'll be doing that in a sample database called EmployeeDB. In step one, I'm going to set up the database, but before I can do that, I need to get into the MySQL prompt. So I'll use this command, enter my password. Okay, now I'm in the MySQL prompt, so I can start to create the database in the table. So the first thing I'm going to do is create the database called EmployeeDB, and then I'm going to make sure that I'm using that database. All right, now we're in the database and we can start to build out the table that we need. So we're going to use the create table command to do that. And we're going to add specific columns. All right, so we've created our table employees that has employee ID, first name, last name, department, salary, and hire date with all different data types. So now we're going to populate that table with some sample data. And we're just going to add sample data that will include items for each of the columns that we have in our table. All right, we've created 5 rows here, so we have 5 records in our table, and now we can start interacting with them. In step 2, we're going to set some transaction and concurrency levels. So the first command I'm going to use is to set the transaction isolation level as serializable. All right, so that query OK tells me that it ran fine. And now I'm going to update the employee's record, and I'm going to use a transaction to do that. So the transaction allows us to start a process, but not complete it until we select commit. So I'm going to start the transaction as the first step. And now I'm going to update the employees, where I'm going to set the salary equal to the current salary minus 5,000 for marketing. So you'll notice that I said update employees and set the salary equal to whatever the current salary is minus 5,000, where the department equals marketing. Now that change is not committed yet, even though we've updated it. It hasn't committed yet because we haven't used the commit command. I'm going to do the same thing for finance, but I'm going to bump their salary by 5,000. So now we've got two changes. Those changes are not in the database. Now I'm going to commit those changes using the commit command. And now they have been committed to the database, and they're a part of the data set. This is very useful when you want to make sure that you're doing changes to your database carefully, and then it allows you to make those changes in a transactional way. I want to unlock my tables. I've got my changes committed to the database. We can use select statements to get data from the database, but we can use some advanced calculations within our select statement to get specifically the data we need. So in this statement, we're going to select from the employees table. We're going to get the first name, last name, and salary. And we're going to select the employees where the salary is greater than the average salary from all the employees. We have a select statement within a select statement. In the parentheses, we have select average salary from employees, and we're going to select those employees where their salary is greater than that average. And this is what it gives us. It gives us three names and their salaries where it's greater than the average from all the employees. In step 4, we're working with a common table expression, a CTE. And this essentially allows us to create a temporary table and then run select statements against that temporary table. And you'll see the output will be a table itself, but it is selecting from the table that we created using this type of SQL command. In this statement, we use department salaries as a temporary table, and that temporary table is made out of selecting the department, the sum salary as the total salary from employees, and then we group it by department. Then from that table, we select all the records from the department salaries which we created. And this is what it gives us. It gives us all the departments, finance, IT, marketing, and HR, and the total salary for all of those individual departments. It grouped them by department. So that type of query allows us to see a very specific view of the data by using that temporary table, or the proper name is the common table expression, to calculate those data. Now in step 5, we're actually going to create a stored procedure. Stored procedures in SQL are little applications, little programs that you can run where you can pass in data and it will send data back. I've got a little tool here that shows me what entities that I have in my database. And you'll see I've got my employee DB database and my employees table. I'm going to click on procedures and you'll see nothing showed up there. We don't have procedures yet. So we're going to use this SQL command to create a stored procedure. And when we create that procedure, then we'll be able to use it to do work. So let me create the procedure using this command. So now we have the procedure called adjusted salary, and we can pass in the department name and the department amount, and then it will essentially run a SQL statement, update employees salary equal to salary plus the adjustment amount, where the department equals the department name that we passed in. So it's a little routine, a little function, and then it will return the results of that function. So now if we refresh our database, you'll see under procedures we have adjusted salary, and we can now use that. We can call adjusted salary from other SQL statements to do the work that's in that stored procedure. So in step 6, we're going to create a function which is very similar to a stored procedure. Functions, you can pass in data and it will return data back. In stored procedures, you're essentially getting a result set back. In a function, you're just getting a value back. In this function, we're going to calculate a bonus based on what we pass in. We're going to pass in the salary, and then we're going to multiply it by a certain number, and then we'll get a value back. So we'll create that procedure. You'll notice under functions, we don't have any functions yet. So we'll run this SQL command. The query OK tells me that the query ran fine. And now when I refresh, we should have that function calculate bonus, which we can now use. We can pass in a salary value. It will multiply that by 1/10 of 1%, and then it will return the value of that bonus. So that's how we can use functions in MySQL. The purpose of this lab was to show you how you can use SQL statements to do all this work. You can create functions, you can create stored procedures, you can call those functions and stored procedures from SQL statements, create tables, add and remove data as well. The SQL query language is very, very powerful for doing all that work.
Securing SQL databases is a fundamental aspect of protecting sensitive information and maintaining trust. SQL databases often store vital business data, personal information, and intellectual property, making them prime targets for potential breaches. Without adequate security measures, databases can be vulnerable to attacks, which can lead to significant data loss, financial damage, and reputational harm. In this video, we will identify the importance of securing SQL databases and describe basic security principles. Implementing strong database security measures brings several key benefits that go beyond simply preventing attacks. Databases often hold valuable information, including personal data, business records, and intellectual property, making them prime targets for attackers. One of the primary benefits of strong security is protections against breaches. Database security minimizes the potential for data exposure, financial loss, and reputational damage by reducing the risk of attacks. Along with protections against breaches, strong security maintains data confidentiality and integrity. Security measures ensure that sensitive data remains confidential and accurate, protecting it from unauthorized access and tampering. Finally, database security is not just a best practice, it's essential for regulatory compliance. Strong security practices help organizations meet legal and regulatory standards, avoid penalties, and ensure compliance with data handling requirements. With these risks in mind, securing access to the database is our first line of defense. So it's time we discuss database security principles, starting with the concept of access control. Access control is the process of managing who can access a database and what actions they are allowed to perform. Access control has two components. The first component is authentication. Authentication is the process of verifying a user's identity to ensure they are who they claim to be. Best practices in authentication involve enforcing strong, unique passwords, implementing multi-factor authentication as an additional security layer, and using single sign-on where appropriate. This way, even if a password is compromised, unauthorized users cannot easily gain access to the database. The second component of access control is authorization. Authorization involves assigning specific permissions to each user based on their role, following the principle of least privilege. This principle means giving users only the access they need to perform their tasks and nothing more. Best practices for authorization focus on applying role-based access control and conducting regular audits to ensure access aligns with user responsibilities. Together, these prevent unauthorized users from accessing the database and enforce strict permissions to limit each user's actions, while access control helps secure who can access the database and what they're allowed to do. Encryption adds another layer of protection by ensuring that data remains unreadable to unauthorized parties. Encryption is the process of converting data into a coded format to protect it from unauthorized access. First, let's discuss how encryption works for data stored within the database. For data stored within the database, known as data at rest, encryption ensures that even if someone gains unauthorized access, they cannot read the data without the decryption key. Databases automatically encrypt database files at rest to protect data from unauthorized access. Now let's consider how encryption protects data as it travels across a network, called data in transit. There are common encryption protocols for protecting data as it travels between the database and application or between servers. Some common examples are Secure Socket Layer, or SSL, and Transport Layer Security, or TLS. By encrypting data in transit, databases protect against interception or tampering as data moves through various network points. Even with strong access control and encryption in place, additional security layers provide a final line of defense to further secure sensitive information. First, regular secure backups are essential for data recovery in case of a breach, corruption, or accidental data loss. By keeping encrypted backups stored off-site, organizations ensure they can restore data without risking exposure. Next, continuous monitoring and logging of database activities helps detect unusual or unauthorized access attempts in real time. Enabling detailed logs and setting up alerts for suspicious behavior enables quick responses to potential security incidents. Monitoring tools can identify patterns that may signal a security threat, providing proactive defense. Finally, firewalls add a layer of protection by restricting database access to trusted IP addresses, preventing unauthorized access attempts. They add a layer of defense to help protect the database from both external and internal threats. In this video, you learned about the importance of securing SQL databases and some basic security principles. In today's data-driven world, prioritizing security is essential for building trust, maintaining compliance, and safeguarding vital information. Protecting SQL databases isn't just about defending data. It's also about preserving trust and maintaining the foundation of an organization's information. As threats evolve, understanding targeted security strategies becomes essential to safeguarding data. In this video, we identify strategies to protect SQL databases from common security threats. The most common threat to databases is a SQL injection attack. A SQL injection attack occurs when harmful SQL code is entered through user input fields to exploit application weaknesses and access or change a database without permission. An injection attack can lead to data leaks, corruption, and major security risks if not prevented. Developers can implement secure coding practices to prevent these attacks. Parameterized queries are one of the most effective defenses against these SQL injection attacks. A parameterized query is a SQL query in which placeholders are used for input values. This ensures that user inputs are treated strictly as data rather than executable code, preventing harmful commands from being interpreted as part of the query. Another method of mitigating SQL injection is input validation. Input validation restricts input types and formats, allowing only expected data. This strategy minimizes the chance of harmful SQL code entering a query, as any input not matching the expected criteria gets blocked. Finally, stored procedures add an additional layer of security against SQL injection. As you've learned, stored procedures are predefined SQL routines stored within the database, allowing only specific approved commands to execute. By using stored procedures, we limit direct SQL interactions, further reducing exposure to unauthorized commands. Now that we have learned how to prevent SQL injection, let's explore another serious database threat: privilege escalation. Privilege escalation is a security technique where an attacker gains unauthorized access to a system with higher permissions than they originally had. This allows them to perform actions they were not initially authorized to do, like accessing sensitive data or controlling the system. To prevent privilege escalation, you can use a strategy called Principle of Least Privilege, or POLP. This strategy helps by granting users the minimum access they need to perform their tasks. Even when permissions are carefully managed, the threat of unauthorized data access remains. Attackers seek any weakness to bypass security and obtain sensitive data, making strong access control essential. To protect against unauthorized access, it's important to add multi-factor authentication, or MFA, to the database management system. With MFA, users must verify their identity through multiple steps, like an additional code or biometric scan, making it much harder for attackers to gain entry with just a password. Another common security strategy for preventing unauthorized access is using single sign-on, or SSO, which strengthens security and simplifies user login. SSO allows users to securely access multiple databases and systems through a single login. It reduces the need to manage multiple passwords and centralizes authentication for stronger oversight and control over database access. Finally, role-based access control, or RBAC, is an important security strategy. RBAC assigns permissions to users based on their roles. By grouping permissions by role, role-based access control helps maintain strict access boundaries, ensuring users can only access the data they need for their specific responsibilities. This setup minimizes the risk of unnecessary data exposure. In this video, you learned about common security threats and strategies to protect SQL databases from them. A robust approach to database security does more than protect information. It builds resilience. By implementing these strategies, organizations not only secure their data, but reinforce the integrity and reliability of their systems. Mastering advanced data handling is crucial for building efficient, secure, and high-performing backend systems. By applying these techniques, from optimizing SQL queries to implementing security best practices, you'll significantly improve your database operations, ensuring both performance and protection in your applications. We began by exploring advanced SQL query techniques, focusing on ways to improve query performance and efficiently handle complex data structures. Next, you examine performance tuning and optimization techniques for SQL queries, helping you identify issues, improve query execution, and enhance overall database performance. Then, you acquired skills in transactions and concurrency control in SQL, focusing on managing multiple user environments, ensuring data consistency, and addressing common concurrency challenges. Next, you gained an understanding of the use of stored procedures and functions in SQL, discovering how to simplify database operations and enhance code reusability. And finally, you received security best practices for SQL databases, exploring methods to protect data, prevent SQL injection attacks, and ensure the safety of sensitive information. By utilizing techniques like SQL query optimization, transaction management, and security best practices, you can enhance the performance and security of your databases, ensuring they run smoothly and effectively. Welcome to using Microsoft Copilot for SQL queries and database operations. This module will show you how Copilot streamlines query writing, optimization, and database management, helping you improve efficiency and easily handle complex tasks. You will begin by writing SQL queries using Microsoft Copilot and examining how it generates efficient and accurate code. Next, you will utilize Microsoft Copilot to generate complex SQL queries, refining your skills in handling advanced database operations. Then, you will use Microsoft Copilot to debug and optimize SQL queries, identifying performance issues and improving query efficiency. After that, you will apply everything you've learned in a capstone project, using Microsoft Copilot to manage practical database operations and complete your final submission. By the end of this module, you'll have the skills to streamline SQL query writing, optimize database performance, and manage complex operations with confidence using Microsoft Copilot. Let's get started with SQL queries and database operations. Writing SQL queries can be time-consuming and error-prone, and that's where the Microsoft Copilot web interface can really help. It provides AI-powered assistance for faster, more efficient, and more accurate SQL queries. So in this video, I'll explain the basic functionalities of Microsoft Copilot for generating SQL queries. So let's go ahead and get started. First, I'm going to access Microsoft Copilot. Now, there's a bunch of different ways you can do this. There is copilot.microsoft.com, as well as there is the Copilot icon down here. But my favorite way is actually through Edge. I think it's the most fully featured of the Copilot implementations right now. So if I pop open Copilot here, you will see Copilot. Copilot is an AI assistant. You put in a text prompt and it will respond text back to you. And so you can ask it to do different things. Like you could just ask it a general question. You could ask it to generate something like code for you. In this case, we're going to generate SQL code. And so these are some queries I'd run before. So you can see your history in here. There's also this button down here at the bottom where you can start a new chat. And typically you don't want to have one big long running chat because these models have what is called a context. So if you leave a bunch of information in there, it's going to sort of be confused. It's like we were just talking about chicken nuggets and now you want to talk about SQL queries. So I always recommend going ahead and starting a new chat. Let's go ahead and ask Copilot our first prompt. We want to have it make some SQL tables. So I'm going to say generate SQL tables. I want 2 of them, 1 for employees and 1 for departments. The employees table should have columns for, let's say, employee ID, name, salary, hire date, and department ID. And you'll notice that I have a bunch of typos in here. Totally doesn't cause a problem with models like this. You can just kind of slug in text and work just fine. I tend to just like write big, long run-on sentences. Totally works. Highly recommend not spending too much time formatting your text. And then the next thing we will say departments should have a ID and a department name. And I will run this. And I was a bit ambiguous here. I said just generate SQL tables, but it actually is sort of smart enough to actually create my SQL statements here that will create these tables. You always want to look to see if it has done what is known as hallucinating. So maybe it made up things that you didn't really want. Maybe it put in something weird, but we can see here we've got a departments table with this int primary key. That makes sense to me. Department name is a varchar of 100. I think that'll work for us. Employees, they've got an ID. Name is a varchar. Salary is a decimal. Hire date is a date. Department ID is an int. And foreign key. Perfect. That looks great. Now, one thing you might want to do here is specify which flavor of SQL you're working with. Maybe you're using Postgres. Maybe you're working with SQLite. Maybe you're working with Microsoft SQL Server. They do have slightly different flavors on the data types and things that they can work with. So that's something to be aware of. It might kick you out some code that you can't quite use unless you give it the context it needs. So in this case, we're just sort of doing this generally. Looks like this would work for something like Postgres. And there are our tables. So now let's say I want to run some queries against this. How about I want the average salary for employees in each department, but only including departments with more than 5 employees. So I will say, write me a SQL query to select the average salary for employees in each department with more than 5 employees. And you can scroll up here. It's not really obvious in their interface, but it sort of kicked us down to this next question. So we see the select average salary for employees in each department with more than 5 employees. Select the department name, average each salary as average salary from employees, join department, group by department name, having count employee ID is greater than 5. Now, this is such a great example of you have the group by, you have the having. This is one of those things where it's really easy to kind of goof these queries up without using a tool like this. Now it's possible there's an error in here. I would always want to run this code, maybe throw some sample data through this and make sure it actually works. But this is kicking out code that we could theoretically use in our application. Now let's say I want employees hired after 2020 included in the results. So we want to filter here. So I'll say add a condition to only include employees hired after 2020. And so now you can see here that we have this, even with a typo, that we are adding this condition to 2020, where e.hiredate is greater than 2020-0101. So this is adding that filter. Now, again, this is really great because I don't have to go into my query, find the spot where I need to change it, and make the change. This is a somewhat simple query, but imagine you're working on some huge brick of like 80, 100 lines, which does happen in SQL queries. And you might have some really, really complex logic going on there that tools like this are really good at parsing. So now let's say I want to get a report that includes each employee's name along with the name of the department they belong to. So I can go ahead and say, write a SQL query to display employee names and their department name. And then I will also say sort by employee name. And so now here is that query. So select e.name is employee name, d.department name from employee E. Join departments D on e.department ID equals d.department ID and order by e.name. It looks like it caught everything we were asking of it. And now these are all times when we're running into sort of situations where we already know what we want. But Copilot can also be really useful if, say, we have some kind of complex join that we don't know how to do. And you can just sort of ask it in plain language to do something for you. So you can say, I'm encountering duplicate results in my joins, but I want single employees. What are some options to handle that? And I can go ahead and send this in, and it will give me some options. I can say use the distinct word, use a group by, use a subquery, use window function. So it will now give me some different options I can look at. And then I might follow up with another question, say like, which of those is the most performant? What are some of the trade-offs of using those different methods? That's where these tools come in really, really useful. If you have a basic knowledge of a tool like SQL, a tool like Copilot will allow you to sort of expand upon that. If you can read it, if you can understand it, if you know it's possible, you can use Copilot to help you implement very complex things that may be beyond what you've done before or what you know how to do or what you're comfortable with. In this video, you learned some of the basic functionalities of Microsoft Copilot for generating SQL queries. With Microsoft Copilot, you have a powerful assistant for querying SQL databases. When working across multiple tables in a large database, tasks like joining tables, running nested queries, and retrieving complex data can be time-consuming to write manually. But Microsoft Copilot can simplify this by quickly and accurately generating advanced SQL queries. In this video, I will describe how to use Microsoft Copilot to generate advanced SQL queries. Let's get started. So here are our tables. We have employees, departments, projects, and employee projects. So employees, departments, and projects are the main tables. An employee project is a join table that joins the employees and projects in a many-to-many relationship. So this means that each employee can be on multiple projects and each project can have multiple employees. Sort of makes sense. So the employees table has an employee ID, a first name, a last name, department ID, hire date, and salary. And it also has this foreign key to the departments based on department ID. We also have the departments table with a department ID, department name, then project with project ID, project name, start date, and end date. So we want to ask Copilot some questions about this information. So now I have this fresh Copilot window open, and I'm going to go ahead and ask Copilot to do something for me. So let's say I'd like help determining the types of joins I'll need based on the data I want to retrieve. So Copilot can help me determine which joins are best suited for the data I need. So let's enter a prompt like you are a SQL expert, which is an example of giving Copilot a persona. By telling Copilot to sort of take on the role of something, it can help it give us better results. In this case, we want sort of the information that a SQL expert would give us, and so this can sometimes be useful. Not always necessary, but definitely worth doing. So let's go ahead and grab our table definitions, and let's say I need a list of employees and their departments, even if the employees aren't in a department. Which type of join should I use? And now it has the table information it needs. Again, you really want to make sure that SQL has all of the context it needs. And in this case, if you were to tell another human to help you solve this problem, they would need to see your table definitions. And so in this case, it says to use a left join, which is indeed what we should do. And not only has it given us the recommendation of use a left join, it also went ahead and gave us some code. And so that is an example of using Copilot to help you determine what type of join to use. And so maybe we want to do something that joins multiple tables. So let's say maybe I want to retrieve employee ID and years of employment along with the department and project details. So in the same chat, I'll go ahead and enter a prompt, something along the lines of write a SQL query to retrieve employee ID and years of employment along with the employee department and project details. And now you'll see that it has come up with this larger, more complex query. We're joining the department IDs, we're joining the employee IDs, and we're joining project IDs. And you can see here that it figured out how to use that intermediate join table that we need to make that many-to-many relationship. This process is really error prone, and so using something like this makes it really easy to set up these sort of more complicated joins like this. And again, this is actually a relatively simple join compared to some of the things you may run into later in your career. And so now that we've talked a bit about joins, let's move on to talk about using Copilot for nested queries and common table expressions. Again, those are also known as CTEs. So if I'm working on a complex query, but I'm not sure whether it needs a subquery or a CTE, that again is something we could ask Copilot to help us solve. So let's go ahead and say something like, you are a SQL expert. Once again, I probably don't need to add that because it already has it, but it can never hurt. So I need to analyze project hours for each employee and compare it to the department average. Should I use a subquery or a CTE? And so here it says we should use a CTE because it would be more readable and easier to manage for this type of query. Then goes on to give us some other information, but I do agree that this is probably the better solution in this case is to use a common table expression. And you can see here that it has come up with a relatively complicated piece of code. Now, especially when you're new, this type of code can take you a long time to write. But I always recommend that when you get a big complicated piece of code like this to make sure you read through and understand what it's doing. We're not going to take the time now to go through line by line and make sure that everything is correct. But know that when you are using Copilot, you always want to check. The bigger the code is that you are getting back, the more you should scrutinize it because there's more opportunities for a small bug or error to sneak in. This is another spot where having testing set up is especially useful. If you have some test data you can run this against to make sure it's giving you the correct results, that can be very, very helpful. But how about another situation where maybe we just want to use a subquery specifically? We already know that. So let's say write a SQL statement using a subquery to select the highest salary in each department. And here we can see that Copilot has developed this query, including a subquery. So you can see down here that we have this subquery nested inside of our larger query in a way that is relatively easy to understand. And now let's throw something a little more complicated at Copilot and see if it can help us with that. So let's say I need to calculate the average project duration across departments and filter for departments with durations over a certain threshold. Write a SQL query using a CTE to calculate average project duration per department and filter departments where the average duration is over 6 months. And so you can see here that it has very quickly come up with an answer. So we can see with project duration as, and so it made this CTE, and here is our final query. Again, with queries this large, always check them, but this seems to have made us something that is probably correct. And with that, navigating advanced queries and complex tables can totally be challenging, especially for beginners. With Microsoft Copilot, however, you can generate sophisticated SQL queries from multiple table joins to nested queries and common table expressions. And these capabilities are invaluable for quickly writing the code you need for data analysis or for a backend. They enable quick and effective insights. By simplifying complex SQL tasks, Copilot allows you to focus on analyzing and applying data insights rather than spending a bunch of time crafting these queries so you can get your analysis and backends together quicker. Errors or inefficiencies in SQL can lead to slow performance or incorrect data retrieval, which can be challenging to identify and resolve manually. Microsoft Copilot is a powerful tool for debugging and optimizing SQL queries. It makes it easier to identify issues and improve query performance. In this video, I'm going to go ahead and explain the functionalities of Microsoft Copilot for debugging and optimizing SQL queries. So let's get started. You can see here I have a fresh window of Copilot open. Again, I always recommend to open a fresh window rather than using a previous conversation so you don't muddy that context. So now we can use Copilot to do things like identify errors in SQL queries. And we can just simply grab a query say like this one that has an error in it, and maybe you'll be able to spot it before Copilot does. So I'll say debug this SQL query. And here it goes ahead and it picks up the fact that we were missing this on statement. So that's a really nice example of somewhere that maybe as you're making a SQL query, you're just having a slow day, or you just accidentally poke something in and you're not able to find it. This is a tool that's really helpful to help you find it. Now, this is a relatively simple example, but imagine you had hundreds of lines in a SQL query, and this does sometimes happen, and that can make it very hard to spot something like a missing piece of punctuation or just one character that's out of place. Copilot can pick up on those things very quickly. Another thing it's very good at doing is picking up spelling errors. This is something that sometimes your coding tools won't pick up on. You meant to say one word and you accidentally said a different word or just spelled it incorrectly. And so if we look here, we have an example with a typo. And so we can say once again, please help me debug this code. And let's see again if you can pick up what the issue is before Copilot. And so it picked up on the fact that we had misspelled salaries. So again, this is a really great example of something that your coding tool might not pick up, but Copilot might. Copilot can also help with logical errors, such as incorrect filtering or grouping. So let's say I have a query that's supposed to retrieve employees by department, but it isn't returning the correct results. So we have that query here. And if we go back over, I can say debug this query once again. And so it's picked up on the fact that we were using a having statement where we should have been using a grouping statement to do our filtering. The having would have been used in an aggregate function rather than running this simple operation where we're not aggregating anything. And so that sort of covers some of the basics where you would want to use Copilot to help you debug your SQL queries. Again, these are relatively small examples, so you can understand them in a quick video, but feel free to just pass really big chunks of code and see if it can help you out. I always recommend testing what you get back, but it more often than not will be able to help you solve your issue. Another place we can explore is optimizing SQL queries. Copilot can provide several optimization suggestions to improve query performance. So let's go back and look at our queries. So we have this next query, and let's say this is running slowly. So I want to say something like, please help me optimize this slow running query. And it picks up on the fact that maybe we want to add an index to this. It also tried to tell us that we should select only the necessary columns to help us reduce the amount of data. And in this case, we are already doing that. That is a common issue with queries. So you can see here that sometimes it's sort of picking up and making up things that aren't actually in your code. This is what's known as a hallucination. So this was sort of picking up on the idea that this is typically something that's wrong with queries, but in this case, it's not something that's wrong with our query. And then you can see here it also has this other proposal for using exists or in to maybe make our query more efficient. Now, this is something I would want to test. Normally, you don't want to go to those kind of lengths to optimize a query unless you're running it a whole lot, where typically will work just fine. And so here it says we have an optimized version of your query, and then they say we have another approach here. So maybe you actually want to run this through some profiling tools and see if it improves your problem. Now, another common use of a tool like this is to help us restructure complicated queries, and this can help us make it easier to maintain our code. So let's go look at our other example there. And so this is a query that it's still relatively small, but it's starting to get a little more complex. So we've got our code in there, and what do we want to say? Let's go ahead and tell it to restructure this query for better efficiency and manageability. And so here it recommends that we use common table expressions and ensure that we have the proper indices. And so here it's saying to create a bunch of indices. Now, I'm not sure we want to create every one of those indices. Again, this might be an example where it's going a little heavy-handed. But you can see here it's actually broken up this query quite a bit. And hopefully this will make it more efficient for us to be able to manage this and think through this process. You can quickly see here that you have these different queries that are then being queried in this larger query. Looking back at our original, you can see that it's a little harder to quickly see what's going on here. And so with that, you've now learned a little bit of how to use Copilot to debug your queries and also
how to help it have you make them more efficient. These again are some pretty simple examples, and I always recommend, when in doubt, just try to throw your code at Copilot and see if it can help, because you very quickly learn whether or not it will be able to help you in that particular situation. It costs you nothing other than a few seconds of your time to copy the code out and put it into Copilot and ask it to help you in the way you want it. In this video, you learned how Microsoft Copilot can assist in debugging and optimizing SQL queries. Copilot is incredibly useful to help you identify and resolve syntax and logical errors. It can streamline performance by helping you find things like indices and making your code more manageable. These features make it easier to manage and optimize SQL databases, which saves you tons of time and ensures reliable, high-performance queries, which is what we're always going for as programmers.
As you have discovered, mastering database integration is essential for efficient and secure systems. The skills you've developed, from using Entity Framework Core to optimizing SQL queries with Microsoft Copilot, are critical for managing complex data operations and ensuring smooth performance. We began by learning about the features of Entity Framework Core and the foundational principles of relational databases. You set up databases, modeled data using EF Core, and performed essential CRUD operations for effective database interaction. Next, you explored the fundamentals of SQL, starting with its syntax and core functions. You retrieved and manipulated data using select, insert, update, and delete statements. Additionally, you worked with the join clause to combine multiple tables and applied SQL functions and aggregate functions to perform data analysis. Then, we examined advanced data handling techniques, focusing on complex SQL queries and performance optimization strategies. You worked with managing transactions, implementing concurrency control in SQL, and utilizing stored procedures and functions. Additionally, you examined best practices for securing SQL databases. Finally, you explored how Microsoft Copilot enhances database operations, from writing and debugging SQL queries to generating complex ones. You optimized query performance with Copilot and applied it in practical database tasks to improve efficiency. Mastering these advanced database techniques and tools is essential for efficient and secure database management. Applying what you've learned from Entity Framework Core and SQL fundamentals to advanced query optimization and using Microsoft Copilot will significantly improve your ability to manage complex data operations, ensuring optimal performance and security in your projects. Congratulations on completing database integration and management.